Every planet is a laboratory we have not yet entered, and every horizon we see through a telescope is a quiet kind of unopened door waiting for heat and pressure to speak. Could alien worlds have crystals, ice fire, or impossible materials? And if so, what lets the universe allow such things to be? On some distant world, water might not soften into puddles at noon. It might harden into a wire that carries current, while thunder crawls through it like a patient animal. On other nights, clouds may not be soft or grey. They may be sheets of metal vapour that condense into needles, falling like slow rain that sings on the rocks. Somewhere, there could be ice that burns in open air, lava that runs as bright as a city's evening windows, and crystals that grow inward like thought, not outward like snow. Welcome to the drowsy astronaut, where we drift a little slower than the day expects, and we leave room for questions to land without hurry. Here we set down the small worries that poked at your attention today. We will wander through materials, the stuff that worlds are made of, and we will ask what happens when heat and pressure push matter into strange corners far from home. So, let us begin. When we say a thing is impossible, we usually mean impossible here, in the narrow street of temperature and pressure that Earth calls ordinary. Think about boiling a kettle and think about ice in a cup. You have a picture in your head for how water should behave, and the picture seems complete. But every substance keeps a menu of behaviors hidden from daily sight. And when the kitchen becomes a volcano, or when a room is pressed to the weight of mountains, that menu flips to new pages. Elsewhere on a world where gravity squeezes the ground like a careful fist, water might act like a slow metal, or gas might wear the habits of a liquid, and your sense of normal would have to wait outside. Start with water, the simplest of our familiar allies. The clear stuff you pour, the soft thing that cools your hands, the patient builder of rivers. At pressures millions of times your room's air, water's molecules no longer keep the same polite distance. The hydrogen can move like a crowded crowd, while the oxygen sits in a stiff lattice. This is called superionic ice, a phase where water is neither liquid nor solid in any comfortable way. The oxygen forms a crystal frame, and the hydrogen flows through it like current through a city grid. Imagine a black block that carries electricity like a wire, hot as a furnace, hard as a stone, yet called ice, because the atoms stand in order the way ice prefers. If you stood with a hand near such ice, you would not see something you could shave into cubes. You would see a glow of heat through a dense, dark body, a thing that hums with the charge of moving ions. The suit you would wear to approach it would have to be a patient machine, cooling you, insulating you, refusing to let your sweat boil or your breath freeze, while your visor shows only a dull sheen in a room without mercy. On big worlds like the Giants, deep inside where pressure writes in capital letters, water likely takes these forms, and the electricity they carry may help build magnetic fields that lean and twist. Jupiter and its kin might keep layers like a cake shaped by storms, with hydrogen turning metallic deeper down and water becoming strange above it, each page of the phase diagram turning without asking for our approval. Metallic hydrogen is another page that refuses to read like a schoolbook. Take the simplest atom, press it so hard that electrons run free, and the substance begins to act like a metal that can carry current easily. On Earth, we play with this idea only in machines, diamond anvils, and pulses that crush for a breath of a second. But in the bellies of giant planets, the pressure is not a visitor, it is the landlord. If you could see it with calm eyes, metallic hydrogen might be reflective like a mercury mirror, flowing like syrup, but shining like a coin, alive with mobile electrons that make a magnetic field possible. Down there, deeper than any mountain can guess, The rules that shape what counts as a solid or a liquid lose their clear borders, and only equations whispered by pressure decide the mood. Let's climb back toward cooler surfaces, because not every alien behavior requires an ocean of weight. Some strangeness appears in the open air, flickering where starlight can still touch the ground. On a world baked close to its star, the day side can be hot enough to vaporize rock. Silicates leave the ground and enter the sky, then condense on the night side in a mineral rain. These are silicate clouds, not fluffy blankets, but vapor made from stone. And when the air drifts across the terminator into cold shadow, the vapor grows seeds and falls as glassy grit. Walk a few steps there, if your boots can take it, and the wind might hiss with microscopic shards that tick against your suit like sand against a window. In some atmospheres, the clouds are made of metals, atoms that on Earth you would hold as wires or foil, but under fierce heat they rise as vapor, then knit themselves into droplets high above. Planets called hot Jupiters can carry titanium oxides and aluminum oxides in their skies, and the sunsets there would paint lines of hard chemistry, not gentle watercolors. The rain might be corundum, the stuff of ruby, falling as tiny crystals that scuff your visor, then melt back to vapor with the morning's return, a cycle that burns without fire and cuts without malice. Stand still, and your suit would ring with a dry, brittle chime, the sound of minerals completing their loop between ground and cloud. Closer to home, yet still far, we talk about ice that burns, not as poetry, but as a simple description of methane trapped in crystal cages. On Earth, we call them hydrates. Water molecules build a scaffold and hold methane like birds in a lattice of twigs. If you warm the cage and touch a flame, the gas burns while ice still sits in your hand. On worlds with cold seas, or crusts heavy with trapped gas, these hydrates might be common, and landslides of burning ice could light the shorelines with blue ghosts that run and vanish. Fire, there would not mean what your mind expects. It would be a quick negotiation between trapped gas and available oxygen, a flash that leaves behind water and wind, with little ash to remember the moment. But alien chemistry permits other fires, tongues of oxidative reactions that do not need our familiar oxygen. Chlorine can oxidize, or sulfur can trade partners, and the glow might be a color Earth rarely sees. On a world with sulfur vapor in the air, a slow burn could creep along mineral beds, not a flame with waving petals, but a crawling front of light and heat that migrates like a thoughtful animal. If you stood a few paces away in a safe suit, the color might be emerald or amber, the smell would never reach you, and the heat would press through your boots like a warning, a postcard from a chemistry set that writes in strange hues. Fire, in that sense, becomes a verb broader than candles or stoves. It becomes the act of energy stepping downhill, choosing a path through bonds, and leaving warmth behind as a receipt. Think about lava, and you might picture red rivers on black rock, slow tongues that reshape valleys and write new maps in weeks. Io, the restless moon of Jupiter, shows us that electric violence can be normal somewhere. Its volcanoes throw curtains of sulfur and sodium into space, the plumes lit by a sun that does not ask questions. Exoplanets even closer to their stars may hold oceans of lava that never cool. Their day sides run with molasses made of rock, and their night sides crack as heat escapes into the long dark. From orbit, you would watch a face that glows like a city turned inside out, a whole hemisphere acting as a stove, with convection cells like beating hearts moving the melt in patient circles. Crystals form anywhere atoms find an orderly compromise, and alien worlds supply more ways to compromise than our neighborhoods do. Under different pressures, different impurities, different timescales, the same elements choose other chairs at the table. Inside Earth, the mineral perovskite and its high-pressure cousin shift the way atoms stack. Deeper still, forms with tighter packing take over, and the crust above floats on this quiet machinery. On super-Earths, where gravity is stronger and mantles are thicker, entirely new families of crystal structures may be the default. Lattices that our labs have only sketched on screens might grow like forests there. Picture a cavern the size of a continent under a pressure that keeps steel from remembering it can bend. Crystals there would not look like museum points. They would look like interlocking frameworks, like cities without streets, each unit cell repeating in stern music. If you chipped away a fragment and held it to a light, it might split the beam into peculiar angles, birefringence turned up to a setting we do not dial at home, colours marching out of what looked like a barren stone. The hardness might make diamond feel suddenly ordinary, not because alien crystals mock carbon, but because pressure and composition can conspire to make other lattices rival or exceed its stubbornness. Wear such a crystal as a ring, and it would not be jewellery so much as a shield, too dense to carve with usual tools, too stiff to polish without patient tricks, too rare to wear except in stories we tell quietly. Onward, the list goes, because what we call rare is often just a local shortage. The galaxy has many shelves, and each shelf stacks atoms with its own logic. Some planets may hold clouds of salt, aerosols of sodium and potassium lifted from hot surfaces. These metals colour flames on Earth, and in alien skies they would colour sunsets you would hardly believe. If wind carries charged grains, the sky could glow with a soft sheet of emission, a sodium layer that acts like a subtle neon sign saying the weather has entered chemistry class. To walk there you would need a visor shield, a glass that filters sharp lines in the spectrum, letting only the quiet light through. Otherwise your eyes would tire as if staring too long at a screen that refuses to dim. Skies then become active instruments, not passive ceilings. They sort wavelengths, they write gradients, they publish the day's reactions for anyone who understands the alphabet of light. At very high temperatures, iron can enter the air in vapor form. In the upper layers of some gas giants, we detect its spectral fingerprints like a signature on a postcard. That means there can be metallic clouds, droplets that act like seeds for further condensation, drifting along wind patterns that never rest, and storms can separate charge like industrial machines, setting up bolts that crack open the night. If a lightning bolt crosses a plume of metal, the plasma would carve a brief tunnel of different colour and different sound, a flash that writes a thin line of altered chemistry from cloud to cloud. Hold your breath in that moment, if your machine allows it, and you would feel nothing but see a change your language might not have prepared you to name. A word about pressure, the quiet hand that enforces most of these changes. It is not just a number. It is a way of organising possibilities. In your kitchen, a cup of water has 3 common phases: solid, liquid, vapour. But draw the axis wider, push down with gravity, lift up with heat, and water unfolds into a library of behaviours. This is the phase diagram, a map where you can walk from one habit to another if you have the tools to move along pressure and temperature. Alien worlds are simply giant laboratories moving along those axes in ways Earth cannot. Maps like this are our travel guides, and when we draw them for mixtures, for rocks, for gases, we discover exits into neighbourhoods with strange streetlights. Now consider ammonia, a neighbour to water in the cold outer reaches. On worlds with ammonia oceans, the freezing and boiling rules are not ours, and the chemistry of life, if it tries, writes in a different tone. Ammonia hydrates build solids that flow like cold toothpaste under stress. and under pressure they may form ionic phases where charge wanders without needing metal wires. Imagine a thin, flexible cable made of frozen salts and ammonia mixtures, its conductivity low but real, its mechanical behavior soft but tough, a cable that could carry the slow heartbeat of a sensor farm buried in an alien glacier. Electrical engineering there would look like knitting, not soldering. A craftsman's art with frozen ropes and patient heat leaks. In deep ice giants, carbon can turn into diamonds that rain inside the planet. Methane breaks apart, carbon finds partners in a lattice, and the crystals fall like hailstones that never reach a street. Laboratory shocks mimic this rain, and we see hints that such processes are not just theories but habits of matter under the right push. The diamonds would likely melt again deeper down, adding to an ocean of liquid carbon that does not sparkle. If you could scoop a handful, you would not see gemstones in velvet. You would see a slurry, a heavy, glittering flow that moves like syrup and drags light in odd ways, a substance both familiar and indifferent to our categories. Riches, in that world, would have no market because value is local, and abundance takes the magic out of any stone, leaving only physics. What would you wear on a world of glass rain? The answer is not fashion, but survival. Layered shields and sacrificial skins like onions of patient material. Your suit would carry an atmosphere of comfort inside, a microclimate where your sweat can evaporate, your breath can exchange, your heart can ignore the vacuum inches away, and the outer shell would be a thing you do not love because it must be destroyed and replaced after every walk. The visor would need to shed shards, perhaps with a faint electric field to push charged dust aside, or with a thin melt layer that heals scratches while you watch tiny lines vanish like fog from a mirror. Gloves would be stiff to resist cuts, yet clever at the fingertips, and tools would be built with lips and flanges that deny grit the right to enter. What would you see where lava oceans breathe under a black sky? Not smoke and flame in the campfire sense, but horizons that glow with a dull intensity, lines of convection sculpting the glare into moving geometry. Above, the air could be a thin soup of vaporized rock, drifting from hot to cold like a courier with no schedule, and the stars beyond would blink a little as light crosses the shimmering layers. The ground would behave like an impatient skin, cracking, healing, fracturing again. You would listen to it with your boots through the suit's contact microphones, hearing a slow music of stress and release. Colors would not be pastel, they would be electric but limited. Red to white in the melt, iron orange in the haze, and the occasional green edge where chemistry finds a narrow window. At the other extreme, cold can build aerogels in nature if chemistry finds the right path. Skeletal solids that trap air and weigh almost nothing, yet hold shape like a memory. A planet's thin mist of silica could deposit into webs along frost lines, building feathery structures that collapse at a touch. Fields of fragile architecture spread like frost flowers across basins that never see a sunrise above the rim. Walking there would be a study in restraint, every step a negotiation with structures that do not forgive. Your path would have to float above on wide pads, spreading your weight like a snowshoe grown into a hover. Silence would be your friend, because sound in thin air is lazy, and the loudest noise would be your own breath, paced against the metronome of suit pumps. The word crystal invites images of clarity and symmetry, but many alien crystals would be opaque, dense, and unkind to light. In the mantle of a super-Earth, grains of high-pressure silicates would align under flow, building textures that guide seismic waves like rails. Their beauty would be mathematical, not ornamental. If you held a polished, slice, you might see bands and fabrics that record the mantle's slow wind, each line a century, each swirl a million years of quiet migration under continents no one will ever map. Time is the mason there, laying patterns brick by invisible brick, while heat keeps everything just soft enough to forget where it was yesterday. Some worlds will wrap themselves in supercritical garments, fluids that are not quite liquids and not quite gases, dense as a shadow, but nimble like wind, filling every crevice with universal patience. Carbon dioxide at the right point becomes such a creature, and on Venus it pushes heat around with brutal efficiency, thick enough to press on you, thin enough to flow, and always eager to carry warmth to any surface that dares be cooler. In such a sea, soluble minerals don't behave politely. They dissolve and precipitate in rhythms set by sunlight and altitude. Cliffs can weep deposits, plains can crust over with minerals that grow like frost but taste like the desert after rain. Breathing there would be a machine's job, never yours. And the machine would whisper in your ear that chemistry owns the air more fiercely than biology ever did. Magnetism shapes materials too, especially when heat allows ions to wander and fields to nudge them. In some clouds, iron grains can align like tiny compasses, building curtains that interact with light. Polarization in such curtains gives the sky a texture, a preference for certain directions that your eyes cannot see but your instruments can, and the sunset becomes a data set, not just a painting. A rain of aligned flakes could produce a shimmer that follows the wind like fish in a current, a collective behavior of small pieces paying attention to a common signal. Physics loves such emergent order, patterns that come free once the ingredients and conditions are right, and alien skies will likely host such quiet parades. Consider the odd phrase impossible materials and notice that it often means materials not possible under Earth's economic or environmental constraints. In other places, they are just Tuesday. Aerometal foams strong enough to build bridges across small canyons might grow where low gravity allows delicate trusses to survive weather. Crystalline frameworks could expand to sizes that collapse here. Self-healing ceramics could be default in crusts that cycle through redox swings every day. Fracture lines would fill with fresh deposits as winds bring reagents, the ground a doctor that closes its own cuts. Clothes for explorers would be woven from local polymers drawn out of atmosphere or soil, stiff at noon, pliable at dusk, with pores that open when heat needs escape, then close again when cold hunts for a way in. On tidally locked worlds, day and night share a hard border, a line where weather fights itself. Materials at the edge will phase back and forth with each eddy of air. Salt that deposits at dawn may sublimate by afternoon, then frost again by moonless midnight. The ground there keeps poor records, always erasing its footprints, always rewriting the same sentence. To sample that edge, you would anchor instruments on arms that reach into both regimes, collecting vapor on one side, scraping crust on the other, measuring the flow of matter across a line that is less a coastline and more a seam. Seams make good laboratories because they make decisions visible, and the planet's grammar of phases becomes a speech you can transcribe. There is a quiet beauty in the way simple rules make complicated landscapes. The equations are short, but the outcomes stretch across valleys. Pressure says sit closer, temperature says move faster, composition says choose a partner, and materials listen without ears, answering by changing shape or state. In that sense, a world is a slow conversation. The crust says one thing, the air replies, the mantle adds a comment, and the star provides the subject that keeps returning. Over time, the dialogue writes cliffs, plains, dunes, and lakes that read like minutes from a long meeting. Reading them is our craft, and every probe we send is a gentle hand asking to touch the minutes, to feel the paper, to see if the ink is dry. Now, what of life, which sees materials as homes, tools, and problems? Could life grow in places with metallic clouds or superionic ice? The answer is not a no, it is a request for patience. Life is adaptable when given gradients of energy and materials that can move and bind. In a world of glass, rain, life might hide under rocks that melt into water for a minute, drinking quickly, then sleeping long. Chemistry can make pockets of safety inside any general harshness. Else, where supercritical seas rule, membranes may look like mineral skins, not lipid films, and information could move along crystals like a whispered note passed down a line of chalk. When explorers design machines for such places, the choice of material becomes the first story beat, not titanium or steel by reflex, but new alloys and composites that borrow habits from the destination. You might bring flexible insulators that endure mineral hail, aerogels that shrug at heat, and thin coatings that hate adhesion so dust gives up. Tools would be like seeds, each adapted, each modest, none pretending to be universal. A visor coating that resists ruby sand would use hard, thin films with self-annealing at microcracks. Boots would mix compliant layers to absorb shards, then stiff grids to spread force, a sandwich that keeps your step honest. Back home, the engineers would measure the scars after each walk, and the suit would evolve version by version, tracing a tiny Darwinian arc through the materials lab. Pressure is the sculptor that never rests. It is the unseen hand that rearranges matter into states our daily lives never require, and our imaginations rarely reach. On Earth, this hand is gentle, giving us rocks and oceans, air, and familiar weather. But on worlds far from here, the same hand presses harder, squeezes longer, and insists on behaviors we call impossible. When hydrogen is compressed until its electrons break loyalty with their protons, the result is a silvery liquid metal, a reflective conductor that flows like mercury, yet hums with currents strong enough to power the largest magnetic fields in the solar system. This metallic hydrogen is likely alive within Jupiter and Saturn right now, creating auroras at their poles, guiding radiation belts, and teaching us that even the simplest element can become extraordinary under the right weight. If you could hold such hydrogen in your palm, you would see not a gas, not an invisible nothing, but a mirror, reflective, almost liquid silver, restless under your glove. It would not stay calm here on Earth's surface. It would revert, explode back into the gas it prefers. But inside a giant planet, pressure cages it into order, making the impossible routine. And so what we call exotic is often just ordinary somewhere else. Matter behaving exactly as the laws allow, but in corners of the universe where the dial is turned past Earth's modest settings. Carbon writes another chapter, because it is both stubborn and versatile. Under ordinary weight, it builds coal, graphite, and diamond, but under the alien push of ice giants, it behaves like a rainstorm. In Neptune and Uranus, methane is common, a molecule of carbon and hydrogen waiting quietly in the cold. Yet under crushing pressure, the hydrogen drifts upward, while carbon atoms fall and bind. They form diamonds in the dark, stones as big as pebbles or boulders, falling through mantles as if hurled by invisible hands, colliding, cracking, then melting into rivers of liquid carbon. To those worlds, diamonds are not treasure, they are weather, a storm of crystals that fall, melt, reform, and fall again in endless cycles, unnoticed except by distant minds like ours. Imagine a sea of liquid carbon, black and heavy, flowing in silence deep within a mantle. No sparkle, no gem-like beauty, only weight, density, and quiet power. A jeweler here calls diamond precious, but in those interiors, abundance erases value. The miracle becomes mundane, the rare becomes rain, and wealth itself becomes meaningless. Sulfur too has its alien habits. On Earth, it coats vents and burns in small matches, but on Io, the volcanic moon of Jupiter, sulfur is a restless spirit. Volcanoes there hurl fountains of molten sulfur miles into space. Plumes stretch outward, illuminated by a distant sun, painting Io's skies in orange and red arcs. Step onto that ground, and you would find a world remade daily. Plains freshly coated in frost one morning, then drowned in molten sulfur the next. Landscapes redrawn as quickly as a restless painter's canvas. Inside your suit, the air would be filtered, but you would know the chemistry was bitter, acrid, a constant etching presence, sulfur vapor licking every surface, staining every rock, insisting on its presence. Now turn your gaze to alien clouds, and forget the comfort of soft, white water vapor. On ultra-hot Jupiters, temperatures near their stars rise high enough to vaporize rock. Titanium oxide and aluminum oxide lift into skies, condense, and form mineral droplets. These metallic clouds shine with iron-grey glints, not fluffy white. Sunsets there are tinted by minerals meant for mountains, storms glitter with shards of metal, and the sky becomes more furnace than heaven. Imagine lightning cutting through those clouds, a bolt splitting vaporized iron, brighter than cities, louder than imagination, a living arc scrawled across an atmosphere that doubles as a conductor. From orbit, such a world would look alive with metallic storms. A globe streaked by glimmering fronts, storms that flash and fade with patterns as alien as the chemistry they ride. Ice, too, is more than water frozen. On distant worlds, it is carbon dioxide, methane, ammonia, or nitrogen, each building its own strange landscapes. On Pluto, nitrogen ice flows like cold wax, slow but steady. Glaciers creep across plains, filling craters, smoothing scars, writing the planet's surface with silence. Stand at the foot of a nitrogen glacier, and you would not hear cracks or roars as in Greenland or Antarctica. You would hear nothing, only the soft patience of molecules shifting position over centuries. Cold is its own sculptor, not as dramatic as heat, but no less relentless, shaping worlds in silence, carving basins and smoothing mountains with a steady hand. The phase diagram is a map of possibilities. Every axis a story of pressure and temperature, every branch a new alphabet of behavior. Earth's water writes only a few chapters, ice, liquid and vapor. But extend the map outward, push harder, heat higher, and water shows superionic phases, supercritical states, amorphous variants. On exoplanets, water settles into these extremes as if they were normal. Oxygen lattices standing firm, hydrogen ions wandering freely, electricity flowing where no wires exist. On Venus, carbon dioxide itself is supercritical, denser than air, mobile as liquid, pressing against every surface, dissolving minerals, carrying heat with ruthless efficiency. In such a sea, the distinction between air and ocean vanishes. Everything is fluid, everything is pressed, everything obeys rules foreign to Earth's mild experience. Crystals tell another story of alien geology. On Earth, we admire quartz and diamond, but in the deep mantles of super-Earths, silicates fold into new lattices, unfamiliar yet stable. These minerals resist melting at unimaginable temperatures, their frameworks stubborn, their grains aligned by the flow of whole mantles. If you cut and polished one of these stones, the light would split oddly, scattering into rainbows Earth's prisms cannot copy. Colours we have no names for, signatures written by alien lattices. Jewellery on such a world would not be ornament, it would be survival. Crystals filtering radiation, channeling heat, stabilizing shelters against alien suns. Fire, too, expands its definition on other planets. It is not limited to oxygen-feeding flames of carbon. On sulfur-rich worlds, fire creeps across mineral beds, slow and green. Chlorine can burn with ferocity, leaving emerald glows behind. Inside your suit, you would see not a dancing flame, but a crawling light. A deliberate line of chemistry moving across the ground, consuming bonds and releasing energy. The word fire there means something broader. Any downhill rush of energy, any rearrangement of atoms that leaves heat as a memory. Deep inside alien planets, every kilometer downward is a new page. Molecules reshaping, bonds breaking, phases shifting, all under the sculptor's hand. Hydrogen becomes metallic, water becomes conductive, carbon reigns as diamonds, silicates fold into strange lattices. Every layer a quiet negotiation between pressure and patience. What we see as exotic is routine elsewhere. What we call impossible is a natural chapter in the book of matter. Every alien material teaches us humility, reminding us that Earth's familiar chemistry is not the limit, only a small excerpt from a much longer story. Ammonia too writes in unfamiliar ink, forming hydrates that flow like toothpaste, soft but stubborn, shifting under stress like pliable metal. Under deeper pressures, these hydrates form ionic phases where charges wander freely, where conduction happens without wires. Imagine cables of frozen ammonia, pliable yet conducting, weaving through an alien glacier, slow circuits of chemistry, transmitting pulses like whispers through ice. Electrical engineering in such worlds would not be soldering, it would be knitting. Cables built from frozen mixtures, woven by chemistry rather than forged by fire. Even the skies are not immune to strange habits. Iron vapor and magnesium vapor have been detected in exoplanet atmospheres, drifting as metallic fogs. Lightning in those clouds would carve tunnels of plasma, leaving arcs unlike anything we know, flashes that briefly rewrite chemistry across whole layers of sky. From orbit, you would see such storms as veins of light across hemispheres, pulses and flashes painting the face of the planet with energy. Storms there are not weather as we know it, but experiments, nature's way of testing what happens when metals take to the air. Salt too may rise into alien skies, aerosols of sodium and potassium lifted from hot surfaces, painting sunsets with unfamiliar spectral colors. If you stood beneath such a sky, your visor would need filters to protect your eyes, sodium lines glowing like neon, potassium hues tinting the horizon in impossible shades. Skies become instruments then, broadcasting their chemistry. Each color, each glow, each emission line a signal waiting to be read. To read such a sunset is to hold a planet's diary, each hue a confession of what atoms drift above. Diamonds rain, metals condense, sulfur erupts, hydrogen shines. Every world becomes a material experiment, every experiment a reminder that possibility is larger than imagination. When explorers step onto such alien soil, their suits will not be garments but laboratories, layered with shields, cooling systems, and coatings to endure glass rain, mineral hail, and toxic winds. Their visors will repel shards with thin fields, melting scratches before they spread. Their boots will spread weight across brittle crusts, resisting fractures that lurk underfoot. Gloves will be stiff but cunning. Tools will be lips and flanges that resist grit. Survival will be less about strength and more about cooperation with the landscape. And yet, in every strange material, life itself could find a foothold. Where glass rain falls, a crack in rock might shelter water for an hour. Where supercritical seas move, a mineral skin might serve as a membrane. Life writes itself where gradients exist, where energy steps downward, where bonds can be rearranged, and alien chemistry offers such gradients in abundance. Perhaps in a lattice of conductive ice, information could move, or in pools of carbon slurry, molecules could test themselves against time. The universe is a patient teacher, and alien materials are its quiet lessons. Every world adds a chapter, every storm a paragraph, every phase change a word, together building a book of matter that we are only beginning to read. Earth is not the template, it is only one version. The rules are the same everywhere, but the stage changes and the actors wear new costumes. What is strange to us is ordinary elsewhere, and what we call impossible may already be the weather in some corner of the cosmos. Gravity is the patient architect that sets the rules. It does not rush, it does not shout, it simply pulls, and over time that pull shapes not only orbits, but the very matter inside a planet. When a world is small, gravity is gentle. Its crust remains light. Its materials stay closer to the forms we know. But when a world is massive, the pull tightens and atoms find themselves rearranged into behaviors no Earth-born chemistry set could reproduce. Super-Earths are the clearest examples, planets larger than ours, yet smaller than gas giants, dense enough to force their mantles into strange architectures. Their minerals shift into phases untested, their surfaces bend under stresses our continents never feel. A silicate crystal here on Earth grows into quartz, but under the fist of a super-Earth's mantle, the same atoms may settle into exotic perovskite frameworks, or tighter patterns still, unfamiliar, opaque, and unbreakable. Think of it as architecture under siege. Bricks rearranged into new designs because the ceiling presses down harder, because the walls lean inward, because survival requires innovation at the atomic level. In those mantles, heat adds its own voice, pushing molecules toward motion, jostling atoms into restless rearrangements. Minerals cycle through phases that resist melting until their frameworks become more stubborn than diamond. If we could bring such a stone to Earth's surface, it would not survive. It would fracture, it would unravel, because the pressure that kept it alive would be gone. These minerals are prisoners of their own depths. Their beauty cannot exist here, because their stability requires the very prison that created them. And so their existence is both certain and invisible to us, hidden in alien mantles, waiting for seismic whispers or spectroscopic hints to betray their presence. But not all strangeness is buried deep. Some worlds reveal their unusual chemistry in plain sight, written in skies we can study from afar. The light of a star passing through a planet's atmosphere is filtered by the molecules there. Sodium writes a yellow line, potassium an orange one, water a forest of dim signatures, and iron a sharp metallic edge. These spectral fingerprints tell us what clouds drift overhead, even when no telescope can see their shapes directly. Hot Jupiter's in particular betray metallic vapors, iron and magnesium glowing in upper atmospheres, proof that heat can lift metals into sky, turning stone into weather and weather into storms far stranger than Earth's. Imagine standing beneath such a sky, your visor flickering with strange colors, your sensors buzzing with unfamiliar emission lines. Every sunset a spectrum, every storm a laboratory in the clouds. Now think about lava, which feels familiar to us. Slow rivers of molten rock carving valleys and shaping islands. On tidally locked worlds, pressed close to their stars, lava never stops. The day side bakes so fiercely that the surface remains liquid, whole hemispheres transformed into oceans of glowing rock. These oceans churn with convection, lifting hot currents upward, dragging cooler ones down, moving like breathing lungs across a planetary scale. Stand in orbit and you would see a hemisphere alive with molten tides, glowing red to white, streaked with cracks that stretch for thousands of kilometers. The night side would be dark, but not quiet. The crust there groans under the cooling, fractures open, and feeds the lava from below. A world like this is less a planet and more a star's reluctant mirror, a body so close it glows with its borrowed fire, never cooling, never resting. Lava itself can shift identity under alien conditions. Silicate melts can blend with unusual impurities, giving colors or flows unknown to Earth. On Io, sulfur-rich lava glows differently, fountains that rise miles high, curtains of red-orange against the black void. On exoplanets closer still, lava may contain exotic oxides or metals, liquids that conduct electricity while flowing as rivers, surfaces where molten rock doubles as a conductor's wire. Such a flow would light up magnetometers as strongly as it lights up eyes, becoming both spectacle and experiment in one endless horizon. And if lava can flow differently, then ice can too. We already know water can freeze into more than a dozen forms, from familiar hexagonal snowflakes to dense, cage-like ices created under pressure. But on alien worlds with colder suns, ammonia or methane form glaciers of their own, creeping sheets of frozen gas that flow as patiently as any Antarctic ice stream. Imagine standing on a plain of frozen methane, the ground shimmering faintly, the horizon flat and featureless. And under your boots, the ice slowly moving, carrying valleys forward at the pace of centuries. Such landscapes are neither land nor sea, but something between, a hybrid environment where solidity is temporary and flow is the rule. Now look upward again, toward clouds made not of water, but of salts, metals and minerals. In the atmospheres of hot worlds, corundum, the crystalline form of aluminum oxide, condenses into droplets. These are the same atoms that, with trace impurities, form sapphires and rubies on Earth. Here, however, the sky itself rains gemstones, tiny rubies falling like hail, grinding against each other in endless storms. From the surface, such a rain would sound like needles against your helmet, sharp and brittle, a constant ticking, a reminder that even beauty can be abrasive when delivered as weather. This is the alien trick. What we admire as precious becomes hazard elsewhere. What we value for rarity becomes abundant, even overwhelming. Exotic crystals may also form inside mantles pushed into existence by unfamiliar pressures. Carbon can create new lattices beyond diamond, predicted structures harder, denser, or stranger still. A super-Earth could hold crystals we cannot name, their symmetries alien, their refractive properties unmatched, their endurance beyond diamond's stubbornness. If you could cut and polish such a stone, It might not shine, but instead twist light into doubled images or hidden colors, a prism of behaviors rather than a jewel of beauty. These alien crystals would not be worn, they would be studied, their very existence proof that matter can always find one more way to arrange itself. Not all alien materials are violent or beautiful. Some are subtle, quiet, and hard to recognize until their patterns emerge. A planet covered in salt flats might seem plain, a desert under dim skies. But salts cycle too, sublimating into air, crystallizing again, forming thin hazes that filter light. A sodium-rich atmosphere could glow faintly, shining with the orange of a neon sign, visible even to instruments across light years. Stand under such a sky, and the horizon would waver with a strange hue. Your visor would dim and filter, sparing your eyes from the sharp lines of light. The planet would speak in spectra, its chemistry not hidden in rock but advertised in the sunset. And in all these possibilities lies a deeper reminder: materials are not static, they are conversations between atoms, pressures, and temperatures. Every alien world is such a conversation, an endless dialogue written in phases and transitions, storms and eruptions, rains and crystallizations. To study these alien materials is not to dream of impossibility, but to listen more carefully to what matter already knows how to do. Heat is another sculptor, just as relentless as pressure. It loosens bonds, agitates atoms, and forces molecules to experiment with behaviors they would never attempt in the cold. On Earth, we know the small range of heat our bodies tolerate, the boiling of water, the melting of metals, the softening of glass. But alien worlds stretch this scale until heat itself becomes an environment, not just a condition. On ultra-hot planets, those baked so close to their stars that orbits last mere days, the heat is so great that rocks themselves vaporize. Mountains do not crumble into valleys, they evaporate into clouds. The sky there becomes a laboratory of stone, a suspension of silicates drifting as vapor, condensing on the night side as rain made of glass. This rain does not refresh, it cuts, it scours, it reshapes the surface grain by grain, and the ground becomes both a source and a recipient of its own material, recycling not through rivers but through winds and condensation. Stand beneath such a storm in a protective suit, and you would hear not the patter of water, but the brittle hiss of shards against your visor. Millions of tiny cuts resisted only by the armor you wear. The clouds above would not glow with softness, they would shine with metallic harshness, reflecting starlight in jagged glimmers. Each droplet is a crystal in miniature, a fragment of rock airborne against its will, and every gust of wind is a sandblaster working on planetary scales. Here, weather itself is geology, skies and crusts exchanging roles, the atmosphere a restless mason carving and refilling its own terrain. Heat also makes metals behave in ways we rarely see naturally. Under high enough temperatures, iron vaporizes, copper and magnesium drift as mists. Titanium becomes part of storms. These are not industrial furnaces, but whole planets wearing the habits of kilns, skies lined with metallic threads, winds that glitter faintly with suspended atoms. A storm in such a world is not a collision of water droplets, but of metals seeking to condense, each bolt of lightning a sculptor, freezing vapor into grains, melting grains back into vapor. The atmosphere becomes a conductor, a restless grid of charge and ions. Storms grow vast, persistent, and violent, their flashes announcing chemistry in motion. From orbit, a planet with metallic clouds would shine as though veiled in quicksilver, a globe shifting in reflective veils, alive with both fire and mirror. Some worlds combine both heat and cold into a single strange rhythm, tidally locked planets that always face their star with one side, while the other lies in endless night. The day side is a desert of fire, crust melted into oceans of lava, atmosphere boiling upward, while the night side is a frozen land, crust cracking from contraction, gases condensing into frost. Between them lies the Terminator, a twilight band where both extremes meet, where storms whip materials back and forth, carrying vapors into cold, dropping ices into heat. Stand on this line and you would see one horizon glowing white-hot, the other black and brittle, and above you, winds tearing endlessly from one regime to another. The materials here are restless, salt freezing and sublimating, metals condensing and boiling, crystals forming and shattering, a seam in space where geology and meteorology are the same. Heat also allows new phases of familiar materials to appear. Water becomes supercritical, ammonia turns into strange hydrates, methane into conductive slurries. At high enough temperatures, molecules lose the distinction between liquid and gas, their behaviors merging, their boundaries erased. A supercritical ocean does not ripple with waves, it seethes, pressing against every surface equally, dissolving and depositing minerals without pause. Venus shows us this directly. Its carbon dioxide atmosphere thick enough to act like liquid air, a dense, heavy shroud that presses as fiercely as a sea. To walk there, if a suit allowed it, would be to stand beneath an invisible ocean, every step resisted, every surface etched, every horizon warped by density. Heat also drives reactions that on Earth we can barely test. In sulfuric atmospheres, sulfates grow and vanish. In chlorine-rich skies, new salts precipitate like constant snow. A single gust could carry grains of chemistry unrecorded in our laboratories, compounds stable only for hours or days before decomposing, yet abundant in alien air. These short-lived materials are no less real. They write the weather of their worlds. They sculpt clouds, coat surfaces, reflect starlight. To an observer, they appear as hazes, veils of color across the atmosphere, skies tinted in yellows, greens, or blues not by water, but by transient molecules. Here, the horizon is never permanent. Chemistry writes and erases in cycles too fast for rock, too slow for flame. Consider the role of light itself, the energy that triggers photochemistry, splitting molecules, creating radicals, initiating reactions. On Earth, light sculpts ozone in our sky, protects us from harsher rays, breaks apart pollution. On alien worlds bathed in harsher suns, light can split methane into carbon and hydrogen, leaving behind smogs of organic haze, thick and orange like Titan's skies. Photochemistry paints those skies with unfamiliar colors, filters starlight, hides surfaces from telescopes, yet also creates molecules that may drift downward, accumulate, and feed further reactions. What we call smog here may be a resource elsewhere, a blanket of chemistry that builds complexity step by step. Heat and light together can forge exotic minerals in air, silicate particles growing into crystalline dust that circulates endlessly. Each tiny grain becomes a nucleus for condensation, a scaffold on which vapors settle, a seed for alien clouds. From a distance, these clouds scatter light into strange colors, deep reds or pale blues, depending on their size and composition. To stand beneath them is to be beneath invisible rain, dust grains falling and rising with thermals, a cycle not of water but of stone. The ground itself bears witness, coated in layers of fine crystal dust, sparkling faintly with each sunrise, swept away and restored by every storm. Let us turn again to lava, for it too teaches lessons when pressed into extremes. On worlds with stronger gravity, lava flows differently, its currents pushed flatter, its floods wider, its reach longer. Eruptions become broader, less towering, but far more covering, their surfaces smoother, their lakes deeper. On lighter worlds, lava leaps higher, fountains reach greater heights, flows tumble quickly into cascades, landscapes remade with dramatic gestures rather than patient blankets. Each world gives its lava its own accent, a different cadence of eruption, a different geometry of cooling and cracking. Lava oceans are not always simple silicate melts. Impurities shift their behaviors, add colors, change viscosity. Iron-rich flows glow differently, their surfaces crusting more quickly, their interiors running hotter for longer. Sulfur-rich flows paint plains in reds and oranges, acrid gases hissing upward, crystals of sulfur dioxide condensing around vents. In exoplanets close to their stars, lava may even carry metal oxides, liquid conductors flowing in loops, adding electrical storms to geological spectacle. Here, even stone can act like a wire, carrying charge as it glows, adding one more layer of strangeness to an already alien surface. Heat also melts ice in alien ways, when the ice is not water, but methane, ammonia, or carbon dioxide. Methane glaciers on Pluto creep slowly, but warm a little, and they flow more easily, rivers of liquid methane pooling in basins. On Titan, methane rains fall from skies, filling lakes and seas, liquids at temperatures where steel is brittle, yet methane is calm and reflective. A methane wave on such a lake would lap gently at shores of frozen organic sand, its rhythm slow, its sound dull in the thick, heavy air. Boats could float, sails could catch winds, but every element would be unfamiliar, every rule written in different temperatures. Heat turns ammonia into new structures, hydrates that shift between phases, some conductive, some pliable, some brittle. These ammonia salts may creep through mantles of ice giants, helping carry heat outward, helping shape magnetic fields. To us, ammonia is a sharp-smelling liquid used in cleaners, but to alien planets, it is a structural material, a building block, a conveyor of energy. Each phase a reminder that context matters, that the same molecule we dismiss here becomes vital elsewhere. We begin to see a pattern in all this. Materials are not defined by their names alone, but by their surroundings. A diamond on Earth is precious, but in Neptune it rains by the ton. Sulfur here is a minor ore, but on Io it is a painter of entire worlds. Water here is life's companion, but as superionic ice it becomes electricity's partner, flowing protons through oxygen lattices deep inside planets. Every context rewrites the identity of a material without changing its essence, only its conditions. And that is the quiet lesson. Possibility is not invention, it is recognition of what already exists under other suns. Matter is never still, it is always listening to its environment. And in that listening, it decides whether to remain solid, to flow as liquid, or to expand as vapor. The boundaries between these states are not absolute, they are choices made under pressure and temperature. And alien worlds are places where those choices take unexpected turns. Every element is a character in this quiet story, each one carrying multiple costumes, each one waiting for the stage to demand a new role. On Earth, we know them in their simplest forms, but under different stars, heavier skies, and stronger gravity, they may act in ways we only describe in textbooks. Imagine then that you are walking across the crust of a super-Earth. The rocks beneath you are heavier, denser, their minerals folded into arrangements that could not survive here. The very ground under your boots might resist cracking, its crystalline lattice locked too tightly to allow earthquakes in familiar styles. Instead, pressure is relieved by flows of strange minerals, creeping underground rivers of silicate slurries. If you chipped a fragment and held it in your hand, it might not glitter as quartz does, but bend light into double images or absorb colors in ways unfamiliar to Earth's palette. These minerals would not survive long in our air. Once pressure is removed, they crumble or shift into softer forms, like prisoners suddenly freed but unprepared for open space. Their existence, then, is conditional, real only in the prison of their mantle, proof that matter can adapt endlessly when gravity insists. Now, let us look upward, toward atmospheres, where materials float as clouds, condense as rains, or flash as lightning. On Earth, our clouds are built of water, small droplets suspended in air. But on hot Jupiters they are built of molten metals, silicates, and exotic oxides. The very rain there could be gemstones, corundum crystals falling through thick skies, bouncing against one another, filling the air with brittle sound. Stand in that storm in a thick suit, and you would hear sharp ticks on your visor, each one a tiny ruby or sapphire striking glass. To such a planet, jewels are simply precipitation, a normal cycle of matter falling and rising, no different from the drizzle we take for granted. Some worlds hold skies tinted by sodium and potassium, metals we associate with street lamps here. When lifted into the air, their emissions glow orange and yellow, painting horizons in neon hues. A sunset on such a world would not fade gently into blue, but blaze in bands of sharp color, an atmosphere written in lines across the spectrum. Your visor would need to filter them, dimming the intensity, sparing your eyes from radiation that burns too brightly in narrow ranges. Here, even light itself becomes a material, divided and shifted, its colors altered by chemistry playing endlessly above. Consider the oceans of methane and ethane on Titan, Saturn's largest moon. There, seas are filled not with water, but with hydrocarbons that flow calmly under skies heavy with haze. If you lowered a hand into such a lake, encased in your glove, the liquid would feel heavier than gasoline, cooler than ice water, smooth and reflective. Waves on these lakes would lap gently against shores of frozen organics, every sound muffled in the dense nitrogen air. To us, methane is a fuel, something to burn. To Titan, it is simply water, the ordinary foundation of landscapes. Such inversion reminds us that definitions are local, that life and geology rearrange their meanings in every environment. Beyond Titan, let us walk across the frozen plains of Pluto, where nitrogen ice flows like glaciers, softening craters over centuries. These glaciers are not brittle, they are pliant like cold wax pushed slowly by invisible hands. Their motion so slow that no human eye would ever catch it. If you placed a marker on the surface, returned 1,000 years later, you would find it displaced, shifted quietly across kilometers of plain. The air above is faint, a thin atmosphere that collapses each winter, snowing its gases back onto the ground. This cycle of sublimation and freezing is Pluto's quiet heartbeat, slower than seasons here, but just as steady in its own frozen rhythm. Now turn inward again, into the mantles of ice giants, where water, ammonia, and methane are crushed together into states without earthly names. Under crushing pressure, water forms superionic ice, a phase where oxygen atoms lock into lattices, but hydrogen ions wander freely, carrying charge like electricity. It looks nothing like ice in a glass. It glows faintly from its own heat, black and dense, humming with moving protons. This phase may be common in Uranus and Neptune, filling layers where magnetic fields are born, fields that tilt strangely, offset from the planet's centers. If true, then electricity there is not carried by wires, but by the restless flow of hydrogen through crystalline frameworks. Such materials push our definitions until they bend. Is it a solid if part of it flows? Is it a liquid if its framework never shifts? Superionic phases are the proof that our categories are conveniences, not laws. Matter can mix its habits when forced, becoming both at once. In laboratories, we glimpse this only briefly in diamond anvil cells or laser pulse experiments, but in alien planets, it endures forever. The universe seems to whisper that impossible is always temporary, that under enough weight and heat, matter invents new compromises. Carbon, too, restless as always, has its alien stories to tell. On Earth it builds diamonds with patience, but inside Neptune's mantle it may rain them without pause, stones falling like hail, shattering and melting in cycles. These diamonds descend, melt into oceans of liquid carbon, then rise again as methane breaks apart in upper layers. What we see as priceless gems are common weather there, abundance stripping away the wonder we attach to them. For a jeweler here, a diamond is wealth. For a world there, it is as unremarkable as snow. Heat deepens these tales, because it loosens the structures of molecules, letting bonds rearrange into unusual orders. On Io, sulfur erupts in fountains, its lava glowing not with the dull orange of basalt, but with sulfur's acrid reds and yellows. Eruptions there spray sulfur dioxide into space, creating thin, temporary atmospheres that collapse again quickly. Walk on Io's plains, and you would cross landscapes painted in bitter tones, streaked with frost that forms overnight, then erased by eruptions the next day. Here, a world is rewritten constantly, chemistry acting as paintbrush, geology as canvas, volcanoes as impatient artists. Other moons like Europa and Enceladus hold oceans hidden beneath thick ice crusts. There, water stays liquid because tidal heating stirs it from below. In such seas, salts and minerals dissolve, forming chemistries we barely predict, let alone understand. Geysers vent these oceans into space, plumes carrying samples we may one day catch with passing probes. If life stirs there, it will be within those oceans, fed by gradients of heat and chemistry, sheltered under kilometers of frozen shield. Every vent is a whisper that habitats need not look like ours. They need only gradients, patience, and chemistry. Some planets wear their strangeness openly in their clouds. On hot Jupiters, aluminum and titanium oxides condense, drifting high, scattering light in harsh colors. These clouds are less like veils and more like shields, thick layers that block starlight, shaping climates below. From orbit, the face of such planets is darkened, not by lack of light, but by excess matter in the air. When storms move, they shift these shields, revealing glowing patches of deeper atmosphere like lanterns uncovered briefly. Salt, too, can join the air, sodium and potassium lifted upward, glowing as emissions that telescopes can detect across light years. Each spectral line is a confession, an admission of what atoms drift in alien skies. We read these confessions patiently, piecing together atmospheres we cannot visit, reconstructing weather we cannot feel. What seems like faint lines in spectra become maps of clouds, storms, and compositions, an astronomy of chemistry rather than light alone. Even in such harsh conditions, the possibility of life lingers at the edges of thought. Not the life we know, but chemistries arranged into order, energies harnessed by molecules, persistence written into alien rhythms. On a planet with glass rain, Perhaps a microbe shelters in a crack, waiting for a fleeting puddle. On a world of supercritical seas, perhaps membranes are mineral, not organic, information moving through crystals instead of DNA. The word life itself bends with these thoughts, stretching to cover not just what is, but what could be. Each of these alien materials tells us that matter is more versatile than we imagine. What seems exotic to us is routine elsewhere. What we call impossible is ordinary in other neighborhoods. Our role is only to listen, to read the signatures written in spectra, to watch the behaviors written in storms, to follow the whispers of atoms under pressure. The universe is a teacher of patience, showing us slowly that every material has more than one face. And as we travel further, we discover that the gallery of possibilities is endless. Every world a chapter, every chapter a reminder that matter is not limited by our imagination. Gravity is a patient storyteller, and its stories are written not in words, but in layers. Layers of atmosphere, layers of mantle, layers of core, each one a page turned more slowly than human lives can measure. On Earth, we see only the surface of such stories, the crust we stand upon, the air we breathe, the waters we cross. But in the bellies of other planets, the tale grows stranger with every kilometre downward. Every added ton of weight changes the rules. Every added unit of pressure demands new arrangements of atoms. And those demands create forms of matter that look impossible only because they are absent from our narrow corridor of comfort. The phrase alien materials does not mean matter disobeying laws. It means matter following them faithfully under circumstances Earth has never offered. Deep inside an ice giant, hydrogen, helium, methane, ammonia, and water mix into states with no clear name, compressed until familiar phases overlap, their molecules locked in restless conversations. At those depths, oxygen atoms may build lattices while hydrogen ions swim freely, turning water into superionic ice, a dark solid glowing with heat, conducting like a sluggish metal. It is neither a liquid nor a solid, yet it holds traits of both. A framework rigid enough to endure, a river of ions agile enough to carry current. We call it superionic, not to exaggerate, but because our categories fail, and so we invent a label that admits we are still learning. Beneath that, hydrogen itself may turn metallic, its electrons freed from atoms, flowing in seas of conductivity. A planet's magnetic field rising not from iron as ours does, but from hydrogen pressed into a form Earth will never hold. The magnetic signatures of Uranus and Neptune already hint at such behavior, fields tilted and displaced, as though the dynamo were not centered but restless. It is the result of a core made not of iron, but of phases so strange that physics itself is forced to write new equations to describe them. And yet these states are not rare. They are likely common across the galaxy. Every ice giant a laboratory of these exotic compromises. Now rise again, out of interiors into skies where chemistry wears its more visible faces. Atmospheres thick with vapors unfamiliar to Earth's meteorology. On ultra-hot planets, orbiting their stars in days instead of years, rocks themselves boil into clouds. Silicates drift aloft, condense into glassy rain, fall into heat, and rise again in an endless mineral cycle. These silicate clouds block starlight, scatter infrared, shape weather that has no equivalent here. For an observer, the spectrum of such a planet glows with fingerprints of stone, metals, and oxides, an atmosphere wearing a mineral cloak. Inside those skies, lightning does not simply strike as it does here, but arcs through metallic vapors, each bolt carving tunnels of plasma, each thunderhead a chemistry experiment in motion. To stand beneath such a storm, protected by a suit, would be to witness both spectacle and hazard, the hiss of glass shards, the glow of ionized metals, the crackle of currents through air, dense with conductive grains. Each strike is a reminder that storms are not only water-driven phenomena, but universal processes of charge separation, waiting only for matter to rise, fall, and rub itself into imbalance. Alien skies obey no other rule than this. They are weather systems written in whatever chemistry the local star permits. Now let us turn to surfaces, the ground itself, where lava and ice share responsibilities in shaping landscapes. On tidally locked worlds, lava oceans stretch endlessly across day sides, glowing as hemispheres of molten rock. The flows move not as rivers, but as seas, their convection cells beating like planetary hearts, their surfaces crusting and cracking as quickly as they form. To orbit such a world would be to see it glow like an ember, its night side cold, fractured, broken, its day side a molten plain, shimmering as though the entire planet were an exposed forge. On lighter bodies, lava leaps differently, fountains rising high in thin air. On heavier ones, lava slumps, flooding wider and deeper, covering surfaces with quiet patience. Sulfur flows add another variation, rivers of red and yellow instead of black, acrid vapors hissing upward, crystals condensing as frost around vents. Each eruption is a performance, matter rearranging itself in public view, chemistry and physics collaborating without pause. And on some close-in planets, lava may even contain metallic oxides, conducting currents while glowing with heat, rivers of molten stone that double as circuits. Opposite this heat lies the quiet hand of cold, shaping landscapes more slowly but no less thoroughly. On Pluto and Triton, nitrogen and methane ices form glaciers that creep silently, filling craters and smoothing plains. These flows are not brittle, they are pliant, soft as wax, capable of erasing scars left by impacts. If you watched from orbit, you would see patterns on their surfaces, convection cells and ridges, evidence of slow but unstoppable motion. Such glaciers remind us that ice is not one thing, but many, each with its own rules, each able to sculpt whole worlds if given time. Some of the strangest states emerge in seams, boundary regions where hot and cold meet, where solid and gas exchange identities. On tidally locked planets, the twilight band between day and night is one such seam. Winds rip across it, carrying vapors from heat into cold, dropping ices into fire, exchanging matter with no pause. There, salts might condense at dawn, then sublimate by noon, then crystallize again under starlight, a cycle repeated endlessly along a narrow belt. To sample this seam, machines would need to anchor themselves, one arm reaching into heat, the other into cold, catching both states at once. These boundary zones are not margins, but laboratories, the very places where new phases appear, the edges where nature reveals her compromises most clearly. Chemistry too plays its role in creating materials that feel impossible. In chlorine-rich atmospheres, flames may burn green, fires creeping along surfaces in crawling waves of light. In sulfur-heavy skies, combustion shifts into yellows and deep reds, reactions slow but relentless, heat moving like an animal across the land. To a visitor, such fires would not resemble campfires or torches, but broad, crawling sheets of energy, heat expanding without flame, light spreading without flicker. Fire itself becomes a verb larger than Earth suggests, any process of energy stepping downward, any rearrangement of bonds leaving heat as a receipt. Life, if it exists, would not ignore these lessons. On a planet of glass rain, perhaps microbes hide in cracks where shards cannot reach, feeding briefly when condensation leaves water or hydrocarbons in small puddles. In supercritical seas, membranes may not be organic but mineral, skins of salt or crystal keeping chemistry inside while ions move across. What we call habitat here may be only one interpretation. Elsewhere, gradients of heat and matter could nurture other strategies. The word life bends, stretching to include possibilities we have not yet tested. Worlds are experiments, each one running with conditions no laboratory can sustain, and each one pushing matter into unfamiliar directions that become ordinary only there. What surprises us is not that matter can behave strangely, but that it always does so with consistency, obeying the same laws whether it falls as diamond rain, rises as metallic vapor, or glows as superionic ice. To move further into the catalogue of alien materials, we must widen our imagination again. Beyond crystals, beyond lava, beyond the more familiar extremes already spoken. There are states still unmentioned, chemistries untested, behaviors that exist not in fantasy but in probability, awaiting discovery in planets we have not yet measured. Let us begin with alloys, because even metals are storytellers under alien skies. On Earth, we build alloys deliberately, melting copper and tin into bronze, or iron and carbon into steel. But on distant planets, the crust itself may forge alloys naturally, under pressures and temperatures that leave no choice. Imagine rain not of a single metal, but of mixed droplets, alloys of nickel and iron, or aluminum and titanium, condensing together in metallic storms. Each droplet carries within it a layered history, metals frozen together into new combinations, falling as spheres, scattering across the surface like beads from a broken necklace. To walk there would be to hear the faint clink of metal against metal, a rain of alloys settling into alien soils. Some planets may hold seas not of water nor of hydrocarbons, but of silicon dissolved in high heat. Silicate melts forming oceans that glimmer with faint metallic sheen. Silicon on Earth is trapped in rocks, stable in crusts, but in hotter, denser worlds, it may circulate freely, dissolved with oxygen, calcium, magnesium, creating lakes of liquid rock far more mobile than any basaltic lava here. Such oceans would not steam with familiar mist, but with vapors of quartz and feldspar, white hazes shimmering in alien suns. Each wave would carry with it shards of crystal, glass forming in foam, breaking, melting again, a cycle of rock behaving as though it were sea. Consider next the alien possibility of polymers, long molecular chains not based on carbon as ours are, but perhaps on silicon, sulfur, or phosphorus. In atmospheres thick with reducing gases, unusual molecules could build chains that form flexible solids, draped across surfaces like tar or rubber. Walk on such a shore, and your boot might sink into pliant mats, neither solid nor liquid, but elastic, bending and recovering, surfaces that resist and yet do not shatter. The air above such landscapes might smell faintly of acrid vapors, the constant exchange of sulfur or chlorine atoms keeping chains unstable, alive with chemical activity. Such polymers would not be industrial inventions, but natural textures, forming alien soils with memory of shape, landscapes that spring back after each step. Beyond polymers, there is the domain of plasma, matter stripped of electrons, glowing with currents and fields. On Earth, plasma is rare outside lightning and stars. But on certain planets, atmospheres heated by nearby suns may hold plasma layers, luminous shells wrapping the globe. Imagine a horizon where the air itself glows faintly, electrons recombining, ions flowing, skies alive with auroral patterns not near poles but across whole latitudes. To breathe, there would be impossible for us, but for instruments, it would be a laboratory, measuring how plasma interacts with winds, storms, and crust. The planet itself becomes a lamp, glowing softly with its own ionized skin, a beacon of strange chemistry visible from across light years. There are stranger paths still. On super-Earths rich in carbon, interiors may push atoms into carbides, compounds of carbon and metals that are rare here but stable under greater pressure. These carbides could build crystals harder than diamond, opaque solids with new symmetries, their refractive indices unusual, their hardness surpassing even our toughest ceramics. If fractured, they might break with edges sharper than glass, splinters that cut at the scale of molecules. A planet dominated by such minerals would be hostile to delicate tools, its dust itself dangerous, its soils filled with powders too abrasive for comfort. Yet those same minerals could also conduct, some carbides acting like metals, carrying current across alien crusts naturally. Other exotic landscapes might emerge from high-pressure salts. Take simple sodium chloride, our table salt, which on Earth forms cubic crystals, clear and brittle. At high pressures inside giant planets, sodium chloride reorganizes, losing its familiar cubic form, stacking into new lattices, opaque and strange. Such high-pressure salts could fill mantles, guiding sound waves differently, altering heat flow, creating geology invisible from the surface. These transformations are not fantasy, they are measured in labs already, glimpses of alien mineral habits inside diamond anvils. But in the wild, on true planets, they endure forever, sculpting internal structures that remain hidden from telescopes. Even noble gases, so often dismissed as inert, may betray their stillness under alien extremes. Argon, neon, xenon, on Earth they float untouched, unwilling to bond. But under crushing force, even they form compounds, clathrates, cages, strange solids where they play roles reluctantly. Imagine crystals where xenon atoms sit trapped in cages of oxygen, stable only under pressure, dissolving the instant weight is removed. These xenon crystals could store gases, transport volatiles, move chemistry between layers of a planet. In such places, the very word inert loses meaning because no atom is beyond persuasion when enough pressure insists. Now turn back upward to atmospheres again, but not hot giants. Consider temperate super-Earths where air may be dense and exotic. Carbon dioxide at many bars of pressure becomes a fluid, not quite liquid, not quite gas, filling valleys like fog, pressing explorers from all sides. Above it, layers of photochemistry could create aerosols of organics, hazes glowing under starlight, cutting visibility into shadows of orange and brown. Walk across such a landscape and you would see only a few meters, shapes swallowed by haze, colors muted by thick filters of suspended matter. The planet would feel endless yet claustrophobic, its air both a shield and a prison. Other skies may shimmer with crystals, suspended like glitter, tiny flakes of salts or ices carried aloft by convection. As winds move, the sky sparkles, sunlight catching grains, flashing briefly before they drift again. The effect from the surface is not a smooth blue as ours, but a restless canvas of twinkles, as though the atmosphere itself wore a cloak of jewels. Instruments would measure constant noise, reflections in every direction, scattering confusing signals, making astronomy from the ground nearly impossible. But to the eye, it would be unforgettable, a world where even air insists on spectacle. Magnetism shapes matter too, building hidden textures in atmospheres. On some planets, metallic grains may align with magnetic fields, curtains of dust and crystals moving in silent synchrony. To observers, these aligned grains could polarize light, giving the sky a directional preference, patterns invisible to the eye but sharp to instruments. Storms could rip and reorganize them, erasing patterns, then rewriting them in new alignments. Another frontier lies in foam, not of soap but of minerals and gases. On some volcanic worlds, rapid cooling may trap gases inside silicate flows, creating pumice-like foams light enough to float in lakes of molten rock. Imagine rafts of stone drifting across lava seas, too light to sink, too brittle to last, breaking apart into dust that coats shores. In atmospheres, mineral foams may form too, aerosols where salts and gases assemble into fragile networks, collapsing at the first touch. Such materials are not solid in our sense, nor liquid, nor gas, but fragile hybrids, ephemera that still shape landscapes. Electrochemistry offers yet another path, alien batteries written into crust and sky. On some planets, lightning may drive cycles of oxidation and reduction, leaving behind mineral veins recharged with energy. Imagine walking across plains where the ground itself holds charge, discharging through your boots, buzzing instruments with constant static. These cycles would not be rare accidents, but daily weather, chemistry powered by constant storms, building and erasing electrical landscapes. A geology of voltage, crust and cloud connected in restless dialogue, materials forming as residues of energy's constant travels. Consider also the possibility of liquid metals flowing openly on surfaces. Mercury here is liquid at room temperature, but imagine a world hot enough for gallium, sodium, or even iron to flow as rivers. These metallic rivers would not glow, but shine, reflective and quick, surfaces broken by ripples that carry gleaming highlights across valleys. Such rivers would conduct electricity naturally, their flows doubling as wires, perhaps sparking storms above as charges shift. To dip a hand in such a stream would be to feel instant ruin, but to watch from orbit would be to see sunlight scattered as blinding flares. Exotic atmospheres may host snow of unfamiliar kind. Carbon dioxide snow falls on Mars, thin, silent, fragile as powder. But elsewhere, snow may be methane, ammonia, or even metals condensing in gentle flakes. Imagine iron snow falling in upper atmospheres, settling into layers, then melting again deeper down, cycling endlessly. Such snow would not sparkle white, but grey, dull, or faintly reflective, a quiet recycling of crust into air, air into crust. Each flake would carry heat downward, contributing to planetary balance in ways invisible to casual eyes. The richness of alien matter is not only in its forms, but in its combinations. Where we think of simple phases, alien worlds layer them, mixing solid, liquid, vapor, and plasma in one restless environment. A lake may be covered in ice, but boiling below. An atmosphere may glow with plasma, but condense into crystals by night. Each environment is a hybrid, a patchwork of states, proof that nature prefers not simplicity but abundance. And every combination adds one more material to the endless catalogue, one more way atoms obey laws in surprising ways. We are only beginning to hear these whispers. Spectra from telescopes give us lines and bands, hints of clouds, storms, crystals, and rains. But as instruments sharpen, as probes cross further into alien skies, we will see directly what until now has been only inference. We will find minerals we never named, phases we never plotted, storms we never predicted, and in every discovery will be the same lesson. Matter is more imaginative than we are, and the cosmos is its workshop. Surfaces are not always the solid platforms we imagine when we think of planets. Sometimes they are seas of molten chemicals. Sometimes they are fragile foams. Sometimes they are frozen sheets so brittle they shatter like glass at a touch. Every world chooses its own form of surface, sculpted by pressure, by temperature, by the materials available, and by the star it orbits. We tend to picture rocky land, but that is a bias of habit. The universe is patient in reminding us that stone is only one way to build a ground. On some planets, the surface is nothing more than a boiling skin above endless layers, shifting constantly, unstable, denying permanence. And on others, the surface is so hard, so dense, that no tool we know could pierce it, the minerals locked into lattices that mock the sharpest of drills. Let us walk carefully across one such imagined world, where molten salt has replaced soil. Sodium chloride, the table salt you scatter over food, melts into a clear liquid under heat, dense, corrosive, and endlessly patient. If a planet is rich enough in such salts and close enough to its star to hold them in liquid state, then its ground is a glowing sea of chemistry. Step in a protective suit, and the ground would sag like a sluggish wave, each boot pressing ripples outward in silence. The air above would shimmer orange, sodium atoms glowing faintly, turning sunsets into fiery bands even in the absence of flame. This world would not carry soil, it would not grow dust. It would simply flow, its surface forever in motion, an endless inland ocean without water. Now shift to colder domains where ices define the ground. Ammonia ice is brittle, crystalline, sharp at edges. If a cliff of ammonia towers above you, it glitters faintly in starlight, pale green like frozen jade. Methane ice is softer, pliant under weight, and a boot pressed into its surface leaves a depression that heals itself slowly as molecules shuffle back into place. Carbon dioxide ice is more familiar. We know it as dry ice, but at higher pressures it changes, reorganizing into opaque cubic lattices, as hard as marble, as sharp as ceramic when broken. Stand on such a plane and the ground would echo faintly under your steps, each sound carrying through a frozen slab that rings like a bell. Still further from warmth, nitrogen ice becomes the dominant sculptor. On Pluto, its glaciers stretch wide, filling craters and smoothing plains. Unlike water glaciers here, they do not groan or crack loudly. They flow silently, reshaping land with patience. A nitrogen glacier may look solid, but under its skin, the molecules slide past each other, behaving more like cold wax than brittle stone. Imagine marking a line on the surface, returning centuries later, and finding it displaced, shifted kilometers away, erased by the flow of frozen gas. This is geology without noise, a world whose heartbeat is too slow for human eyes, but steady enough to rewrite continents given time. Not every alien surface is made of crystals or ices. Some are soft, pliant, and elastic, built from long molecular chains. In reducing atmospheres, exotic polymers may form naturally: silicon chains, sulfur chains, phosphorus-based backbones, tangled into mats and sheets. Walk across such a plane and your boots would sink slightly, the ground bending under weight, then recovering slowly, like rubber stretched and released. The air would carry sharp chemical odors, acrid reminders that bonds are unstable, constantly rearranging, keeping the material soft and restless. Such polymeric grounds would not be permanent. They would erode, melt, reform. Landscapes with memory, surfaces that remember each step before springing back. Other worlds may build foams, fragile networks of minerals and trapped gases. On volcanic planets, silicate foams may form, pumice-like stones light enough to float even on molten lakes. Picture rafts of stony foam drifting across lava seas, breaking apart slowly, scattering brittle fragments along fiery shores. On worlds with denser atmospheres, mineral foams could rise into air, aerosol networks that collapse at the faintest touch, invisible until sunlight glints across their thin structures. Such landscapes are neither liquid nor solid, but hybrids, fleeting materials that crumble almost as quickly as they form. Imagine instead metallic rivers, where gallium or sodium flows freely at surface temperatures. These rivers do not steam, they do not glow, they simply shine, reflective, quick, bending light as rippling mirrors. To stand beside such a metallic stream is to watch sunlight scatter in dazzling flares, every ripple a flash too bright for unshielded eyes. These flows would conduct electricity naturally, linking storms in the sky to charges in the crust, connecting atmosphere and ground through silent circuits. One bolt of lightning above could send arcs dancing along the metallic surface, light racing sideways before diving underground. Beyond surfaces lies the air, and air itself is no less strange when conditions are different. Some planets carry dense atmospheres filled with aerosols, hazes of organic compounds that glow orange, filtering starlight until landscapes vanish into twilight. Others carry skies filled with crystals, tiny grains of salt or ice suspended aloft, scattering light into restless glimmers, a perpetual sparkle instead of a smooth dome. Walk under such a sky, and every movement would be accompanied by flickers, every step catching grains and sending them upward again, each sparkle another reflection of the star above. The atmosphere becomes a restless cloak, not transparent but alive, a veil shifting constantly with winds and convection. There are even worlds where snow is not water, but metals. Iron snow, condensing in upper layers, falls as dull flakes, sinking deeper until heat melts them again, cycling endlessly between air and core. Such snow does not glitter white, it glows faintly, reflective, grey and heavy, grains sinking quickly through thick skies. To stand in such a storm would be to hear the faint hiss of heavy particles falling, striking ground without melting, piling into drifts of metal. This cycle of iron precipitation is not poetic, it is functional, transporting energy, redistributing heat, maintaining planetary balance. Exotic minerals may dominate surfaces where carbides form, compounds of carbon with metals like titanium or tungsten. These carbides are harder than diamond, opaque and unyielding. A planet covered in such minerals would be hostile to drills, its very dust sharper than knives. Even fractured, these minerals split into splinters, with edges so fine they cut on contact, a hazard to machines, a challenge to any shelter. Yet their properties also include conductivity, thermal resilience, chemical stability. A planet built of carbides is both a fortress and a laboratory of toughness. Here, even dust is dangerous, abrasive grains filling the air, grinding against instruments, eroding any unprotected surface. In other places, salts dominate, but not in the cubic, transparent forms we know. At high pressures, sodium chloride reorganizes, its crystals becoming opaque, stiff, new symmetries emerging that Earth's crust never demands. Such high-pressure salts could fill mantles, altering sound speeds, guiding convection, shaping magnetic fields indirectly. On the surface, they might never appear, but deep within, they define how heat flows, how energy moves, how planets evolve. What we call ordinary salt may be only one of its many identities, its true diversity hidden by Earth's modest limits. Even noble gases abandon their inertness under alien extremes. Argon, neon, xenon, atoms we call silent, bond under pressure, forming clathrates and cages, crystals with trapped guests. Picture xenon atoms locked in oxygen lattices, unwilling partners stable only in high-weight prisons. These crystals may act as reservoirs, storing gases, releasing them slowly as pressures shift, feeding atmospheres across geological timescales. On such worlds, even noble gases are not idle, even they are enlisted into the work of geology and weather. Some planets present seams, twilight zones where hot and cold exchange matter endlessly. On tidally locked worlds, this seam is a permanent line, one horizon glowing with lava, the other black with frost. Here, salts condense and sublimate daily, metals vaporize and settle, crystals grow and vanish, all in cycles too quick to map but too steady to deny. To stand there is to see contrast written into the landscape itself, a frontier where nothing stays in one phase for long. The seam is not a boundary, but a laboratory, the place where states mix and compromise, where new materials emerge in each gust. Lightning plays its part too, sculpting matter into fleeting forms. In mineral-rich skies, bolts carve tunnels of plasma, leaving new compounds frozen in their wake. Some of these products are ephemeral, breaking apart in hours, others remain, coating grains, painting clouds. The flash itself becomes chemistry, a sculptor as fast as it is violent, writing new materials across kilometers of sky in a second. Each strike is a reminder that energy always leaves traces, that even violence builds as well as destroys. Alien surfaces and skies show us that the word material is far broader than Earth suggests. Liquids are not always water, ices are not always frozen H2O, solids are not always silicates or metals. Every world chooses from the same periodic table, but the recipes differ, the ovens hotter or colder, the pressures higher or lower. And each recipe gives rise to new textures, new landscapes, new cycles of matter. The more we explore, the clearer it becomes that there is no single definition of ground, sky, or weather. There are only local arrangements, each obeying universal rules in their own context. Change is the only law that matter never refuses. And on alien worlds, the pace and style of that change often escape every expectation we carry from Earth. A planet is not a static sculpture, it is a restless machine. A cauldron of chemistry and pressure, a furnace and a freezer, each layer a negotiation between forces. To study alien materials is to study the art of compromise, atoms compromising under heat, bonds compromising under force, phases compromising under time. Each compromise gives rise to a new form, a new face of matter that is both temporary and eternal, fleeting in its state yet endless in its repetition across galaxies. Let us begin with perovskites, crystals that may be exotic to us but are likely common under alien conditions. A perovskite is a structure where oxygen atoms form cages and metals sit inside, locked into repeating lattices that resist melting even at colossal temperatures. On super-Earths, these lattices may fill whole mantles, replacing silicates we take for granted with sturdier, denser phases. The hardness of such crystals surpasses many minerals we know, and their electrical properties may allow conduction or magnetism in forms untested here. Imagine walking across a plain of fractured perovskite, shards glinting not like glass but like matte ceramic, light scattering dully, heat radiating upward in waves. Beyond perovskites are the stranger carbides, compounds of carbon with metals such as titanium or tungsten. On Earth, they are laboratory products built for drills and armor, but in carbon-rich worlds they may be native, entire crusts composed of opaque metallic hard carbides. A carbide plane would be unyielding, sharper than glass at its edges, splintering into flakes capable of cutting machines that dared to land. The dust alone would be hostile, grains so abrasive that they would erode metal surfaces, clog joints, and grind optics into blindness. And yet these same carbides could carry current, making the crust of such a planet both a fortress and a circuit, a geology of endurance and conduction. Sulfides write another chapter, for sulfur bonds eagerly with metals under heat. Iron sulfide, nickel sulfide, copper sulfide, all may be abundant in alien mantles, creating crusts that shine with metallic colors, unlike anything here. Picture a land where the soil is dark and iridescent, each grain catching starlight with flashes of green, blue, and gold. A glittering desert of fool's gold that is no fool at all. The smell of sulfur would be acrid, sharp, filling the air with bitterness, a reminder that these compounds are alive with reactivity. Volcanoes on such a world might erupt not basalt but sulfide-rich lava, black rivers that cool into shimmering, reflective plains. Exotic salts extend the story further, because even the simplest halides change under alien conditions. Sodium chloride, the familiar salt of our tables, reorganizes into new lattices under immense pressures, forming opaque solids harder than its common cubic form. Potassium chloride, magnesium chloride, and stranger cousins may dominate whole crusts, turning surfaces into brittle, crystalline landscapes. A salty desert there would not crunch as ours does, but shatter under boots, shards slicing upward with each step, surfaces more dangerous than sand. Such high-pressure salts would not sparkle, they would dull the light, scattering it unevenly, giving the landscape a muted, eerie glow. Now shift to noble gases, the atoms we call inert, the atoms we assume refuse companionship. Under crushing pressure, even xenon forms compounds, binding reluctantly with oxygen or fluorine, becoming stable crystals, only in the prisons of giant planets. These crystals may act as vaults, storing gases that later escape as atmospheres thin or crusts fracture. Imagine veins of xenon ice buried deep, glowing faintly under stress, waiting to dissolve when pressure releases. Some surfaces may be built from exotic glasses, silicates cooled too quickly to crystallize. On Earth, we know obsidian as a volcanic glass, sharp, dark, and smooth, but on alien worlds, glass planes could stretch for hundreds of kilometers. These planes form when lava seas cool in sudden storms, their surfaces freezing smooth before convection can sculpt them. Step on such a plane and your boots would ring, echoes traveling long distances, sound carrying like it does across sheets of steel. Cracks would sparkle with reflected light, each fracture a blade waiting for careless steps. Elsewhere we may find foams of rock, pumice-like materials filling lakes, rafts of stone floating on molten seas. On some volcanic planets, gas escapes lava so quickly that entire surfaces are covered in frothy rafts, drifting and colliding in slow motion. These foams may travel for decades, breaking, reforming, carrying minerals across continents. To stand on such a raft is to stand on fragile balance, the ground beneath creaking, shifting, threatening to collapse into liquid fire. The air would taste of mineral vapor, sulfur, and chlorine, each breath a test for even the strongest suits. Atmospheres themselves can crystallize, producing rains of unfamiliar snow. On Mars, carbon dioxide falls as frost, delicate, transient, vanishing with sunlight. On colder exoplanets, methane snow may fall thick, forming drifts meters deep, soft, pliant, creaking under weight. Further still, ammonia snow builds mountains, flakes stacking into hard cliffs, glinting pale under faint suns. And in the hottest of skies, iron or magnesium may fall as metallic snow, dull flakes drifting downward only to melt again below. Magnetism sculpts materials too, not only fields. In mineral-rich atmospheres, metallic grains can align with magnetic lines, drifting in curtains, polarizing light in unusual ways. An observer might watch as the sky itself tilts polarization, shifting with storms, repainted invisibly with every solar gust. These grains are tracers, following the threads of unseen forces, forming clouds and veils shaped less by wind than by magnetism. The result is a sky that is half material, half force, a canvas painted by electricity as much as by matter. Electrochemistry creates landscapes that are not static but charged. On some worlds, constant lightning builds reservoirs of energy underground, driving cycles of oxidation and reduction. Soils may hold charge like a battery, discharging through rocks and rivers, buzzing instruments with static fields. Every surface becomes a wire, every storm a generator, every riverbed a conductor. Such planets are not quiet geologies, they are restless batteries, storing and releasing energy in cycles that shape their chemistry. Even oceans can stray from water. On Titan, seas of methane and ethane stretch under thick haze, calm, reflective, carrying waves only centimeters tall. On other worlds, seas may be ammonia, heavier, denser, faintly green, carrying bubbles of nitrogen that burst slowly. Further still, carbon-rich planets may hold seas of liquid hydrocarbons thick as tar, black mirrors that drink starlight instead of reflecting it. Stand on a shore there and the sea would suck light away, horizon and water indistinguishable, silence stretching in all directions. Consider now the possibility of rivers of liquid metals. Mercury flows at room temperature, gallium melts in the hand, sodium liquefies under heat, but on exoplanets far hotter, iron itself may flow openly. An iron river would not sparkle red as lava does, but gleam silver, reflecting light so harshly that visors would need heavy filters. Its surface would ripple with blinding flares, each wave a mirror scattering starlight. Such rivers would be silent except for the hiss of cooling edges, carving metallic valleys, reshaping crust as though geology itself were a foundry. The very dust of some worlds may be exotic. Instead of silicate sand, some planets may have carbide dust, sharp and cutting, or salt dust, corrosive and bitter. In strong winds, these grains would scour surfaces, polish rocks, etch cliffs, and wear down machines. Each storm would be a sandblaster, a moving wall of destruction, carving landscapes into alien geometries. But to the eye, such storms would glow faintly, metallic grains reflecting light, sparkling in veils even as they destroyed. None of this is fiction, it is probability. The laws of chemistry allow each of these states, each of these behaviors, given the right conditions. And because there are billions of planets, every possible condition will eventually be tried. Our task is not to imagine wildly, but to recognize patiently that matter has already explored every option we can describe. Each alien world is another test, another demonstration of what atoms are willing to become when stars demand variety. And so the gallery of alien materials continues, vast, endless, spilling across exoplanets like an unending encyclopedia. Every spectrum we measure is a line in that book. Every storm we detect is a paragraph. Every strange crystal we predict is a word waiting to be confirmed. The story is not over. It cannot be over because the universe never stops writing. Matter is the pen, energy the ink, time the paper. and the book is larger than our ability to read. So we continue, not closing chapters, but turning pages, searching for the next entry in this infinite dictionary of states. Pressure is only one half of the sculptor's hand. The other half belongs to temperature, and together they write phases of matter that refuse to appear under Earth's mild sky. Where pressure dominates, atoms are forced into proximity. Where temperature dominates, bonds are torn apart, and in between the two lies an unstable territory where both demands are honored uneasily. Planets live in this territory. They are crucibles that never cool, test chambers that never stop, and what they produce are materials that we have not yet named. Some of the strangest are supercritical fluids, states that ignore the line between gas and liquid. Carbon dioxide becomes such a fluid on Venus, where pressure presses as firmly as oceans and heat stirs as violently as deserts. This sea of gas does not ripple, it seethes, filling every gap with weight while flowing with the freedom of air. A probe sinking into such an ocean feels resistance from every side, crushed as though by water, yet still moving through molecules free to slip like wind. To stand there in a suit would be impossible. Every seam pressed inward, every joint straining, every surface covered with frost that forms and vanishes in seconds. Other gases also form these supercritical states: methane on cold worlds, ammonia on distant moons, hydrogen on massive planets. Each one obeys the same rule. When temperature and pressure rise together beyond a boundary, liquid and vapor vanish as categories. There is only one fluid, dense, restless, efficient at carrying heat, dissolving minerals, building new chemistries in silence. A valley filled with such a fluid would look empty from above, but inside it the horizon would vanish, light bending, sound muffled, matter dissolved into its own breath. Beyond these fluids are plasmas, stripped atoms glowing with the energy of separation. On Earth, plasma lives in lightning and stars, but on hot worlds, it may float in atmospheres, layers of ionized air that shine faintly even without storms. Imagine walking beneath such a sky, your visor catching a dim glow not from sun, but from the very air around you. Currents ripple across these layers, invisible rivers of electrons bending under planetary magnetic fields. Lightning in such places does not strike as bolts. It spreads in curtains, sheets of light rippling across horizons, chemistry sculpted in the language of charge. Magnetism guides matter as much as pressure, and on some planets, metallic grains in the air align like iron filings on paper. The sky itself becomes polarized, scattering light differently in different directions, a secret pattern invisible to the naked eye but measurable by instruments. Storms tear these patterns apart, winds rebuild them, solar gusts repaint them, so that the very air becomes a moving canvas of invisible geometry. To live there would be to live inside a compass, every breath and every gust hinting at the direction of unseen fields. In deeper crusts we find phases of minerals stranger still. Silicates rearrange into perovskite structures, oxygen cages locking metals into grids so stable that they resist melting near the heat of stars. Carbon bonds into carbides, titanium carbides, tungsten carbides, each one harder than diamond, denser than steel, opaque and unyielding. A planet made rich in such compounds would wear a crust of armor, its dust sharper than knives, its mountains harder than any blade forged on Earth. Machines would erode quickly in such dust, every moving part scarred, every lens scratched, every joint ground into failure. Even salts, so familiar here, become exotic forms under pressure. Sodium chloride, our common table salt, rearranges into opaque crystals, their lattices tighter, their properties altered beyond recognition. Such high-pressure salts may dominate the mantles of super-Earths, guiding heat flow, shaping convection, altering magnetic fields. They may never appear on surfaces, but deep within, they define the very behavior of planets, deciding whether energy escapes slowly or erupts suddenly. The word salt there carries a weight we do not yet imagine because it does not mean seasoning, it means structure. Snow too can betray us because not all snow is water. On Mars, carbon dioxide falls as delicate frost, but elsewhere methane forms flakes, piling into dunes, shifting with winds across frozen plains. Ammonia snow is harder, stacking into cliffs, flakes pressed into structures as stiff as rock. And on hotter planets, iron itself may snow, dull metallic particles drifting downward, melting as they descend, cycling endlessly between air and mantle. Such snow would not sparkle, it would glow faintly, reflecting starlight in muted flashes, filling valleys with metallic silt. There are surfaces built of glasses, frozen too quickly for crystals to form. On Earth we know obsidian, dark volcanic glass, but on exoplanets whole plains may stretch smooth and brittle, products of lava oceans cooled in storms. Walking across such a plain would feel like walking on steel, every step ringing far, echoes carrying kilometers across unbroken sheets. Cracks would gleam with sharp reflections, splinters lying in wait for careless feet, each fracture a blade carved by sudden cooling. These glass plains are not rare accidents, they are routine results of heat and quenching cycles on volatile worlds. In atmospheres, aerosols form strange hazes. On Titan, methane photochemistry builds orange veils, but elsewhere chlorine or sulfur may form green mists, painting skies with alien colors. These hazes scatter light differently, turning stars into blurred halos, hiding surfaces behind translucent curtains. Each particle is a tiny reactor, chemistry frozen mid-step, waiting for sunlight to trigger its next transformation. Breathe such air without filters and your lungs would burn, not with heat but with chemistry, every breath a violent compromise. Dust itself can be exotic, not silicate sand, but carbide or salt grains. Storms on such worlds are sand blasters, walls of abrasive powder carving cliffs, eroding machines, wearing everything into alien shapes. From orbit they would shine faintly, metallic dust reflecting starlight, storms glittering as they devoured surfaces. On the ground they would roar, every gust a scouring hand, every grain a knife. Such landscapes are not only dangerous, they are dynamic, sculpted hour by clouds of cutting particles. In other places, rivers may flow not with water, but with metals. Mercury flows at room temperature, gallium melts in the hand, sodium liquefies under moderate heat, and on hotter exoplanets, even iron may flow freely. An iron river gleams instead of glows, scattering light harshly, blinding to eyes unshielded. Its ripples move like molten mirrors, every wave a flash, every eddy a flare of brilliance. To stand beside it would be to watch sunlight explode across currents, every moment a storm of reflections. Volcanoes too change their voice on alien ground. On Io, sulfur erupts instead of basalt, fountains of molten sulfur leaping miles high, freezing into colored snows before falling back. Other planets may vent chlorine-rich lavas, glowing green, acrid gases rising in sheets that corrode every surface. These eruptions are not exceptions, they are rules of geology in places where chemistry differs, proof that volcanoes are not always black and red, but can be painted in a wider spectrum. Even noble gases abandon their quiet reputation. Xenon bonds reluctantly with oxygen, argon with fluorine, under pressures that crush cages into stability. Crystals of these gases exist deep in giant planets, cages storing atoms, releasing them only as pressures change. The word inert is a convenience on Earth, but not a universal law, because even noble atoms yield when the weight of atmospheres demands. Matter does not care for our categories, it cares only for balance. And under alien skies, balance is found in bonds we never expect. Electrochemistry reshapes alien crusts into batteries. Constant lightning drives reactions, charging soils with potential, oxidizing metals, reducing salts. A traveler walking there would feel discharges through every step, static leaping from rock to boot, instruments buzzing with interference. The ground is alive with current, a silent network of charge spread across kilometers. Such planets are restless batteries, geology and weather connected by constant pulses of electricity. Some worlds carry seas of hydrocarbons, thicker than oil, blacker than tar. On Titan, methane and ethane fill lakes, but on carbon-heavy exoplanets, whole oceans may stretch dark and endless. These seas do not sparkle, they absorb, each wave swallowing light instead of scattering it. A horizon above such a sea looks like ink poured across the sky, reflections vanishing, starlight consumed. Boats could float, sails could catch wind, but every surface would return coated in black film, hydrocarbons clinging stubbornly. Not all materials are destructive or hostile. Some are delicate, fleeting, barely stable even where they form. Short-lived crystals grow in volcanic plumes, condensing for minutes before decomposing again, their shapes never captured except in traces. These ephemeral materials coat rocks, tint snows, scatter light, yet vanish almost as soon as they appear. To study them would be to chase ghosts, to catch what dissolves as soon as air changes. Yet they matter because even ghosts shape climates, scattering starlight, cooling skies, altering chemistry with each brief visit. There are also materials born of impact, the violence of collisions sculpting new phases. When asteroids strike worlds, heat and shock melt crusts, force atoms into unnatural arrangements, build glasses, shatter minerals, create diamonds instantly. Some impacts may press so hard that exotic phases appear, stable only under that violent second, vanishing as soon as pressure releases. But traces remain, minerals we call high-pressure polymorphs, witnesses to events that shook entire planets. On alien worlds with heavier bombardment, such minerals may dominate surfaces, entire plains built from matter frozen in shock. Everywhere we look, alien materials remind us that variety is the universe's first language. Solids, liquids, gases, plasmas, hybrids, short-lived ghosts, eternal lattices. Each one obeys the same laws, but each one sings in a different voice depending on where it resides. The catalogue is not small, it is infinite, because every planet pushes the same atoms into new conditions, new behaviors, new compromises. And what we call strange is only strange because we are not there to see it daily. To those worlds, each material is not exotic, but simply normal. Let us press further still to stranger phases, stranger skies, stranger crusts, because matter is not finished and neither is our observation. Weight is more than gravity, it is the way a planet teaches matter new manners, forcing every atom to decide whether it will bend, break, or rearrange. On some super-Earths, the weight of overlying layers is so extreme that common molecules collapse into unexpected cages. structures known as clathrates where one atom hides inside a framework of others. Methane clathrates on Earth are fragile, they melt at modest heat, but under alien pressures they may remain stable for eons, locking gases away in crystal vaults until geology cracks them free. Imagine walking across a frozen plain that is not ice but a lattice filled with methane, every step pressing faint tremors into cages holding invisible guests. When a fracture spreads, whole valleys may exhale suddenly, plumes of methane bursting upward, igniting if the air is rich with oxidizers, silent if it is not. But clathrates are only one expression of hidden architectures. On planets with exotic mixtures, neon or xenon may slip into these cages too, their unwilling companionship secured by nothing more than brute pressure. Such crystals would look dull to the eye, but spectroscopy would betray their secrets, absorption bands shifted by atoms that never belonged there. These hidden gases are planetary reservoirs, banks that store atmospheres until tectonics cashes them out, altering climates in sudden shifts. To predict such events is nearly impossible because stability is a balance, and alien balances are often precarious. Other surfaces may carry polymer skins, long chains of silicon or phosphorus winding into sheets that drape across crust like tarps. Unlike earthly plastics, these skins are not synthetic. They form spontaneously when ultraviolet light breaks apart gases, stitching fragments into chains. Over centuries, layers accumulate, rubbery planes stretching for hundreds of kilometers, cracked into plates by contraction, softened again by new deposits. Step onto such a landscape and your boots would press into flexible mats, elastic ground sagging then rebounding, sound deadened as though muffled by carpets. The polymers would not decay easily, resistant to further light, resilient against cold, a surface built of chemistry's stubborn leftovers. Superconductivity might emerge naturally under conditions no human laboratory can sustain. At ultra-high pressures, hydrogen-rich compounds align into phases where electrons flow without resistance, their quantum dances uninterrupted by vibration. A planet's mantle could carry such a superconducting layer, hidden kilometers down, its currents wrapping the world in magnetic shields stronger than Earth has ever known. If such currents couple with convection, auroras might blaze across entire hemispheres, the whole sky alive with sheets of colored fire. From orbit, the magnetic field of such a planet would appear distorted, immense, its reach stretching farther than the orbit of moons. Radiation too sculpts matter into exotic forms. On worlds bathed in constant stellar flares, organic molecules may never survive intact, yet radiation stitches their fragments into resistant aromatics, layered like asphalt. These radiation-forged soils are dark, brittle, sharp-edged, their surfaces crackling with electrostatic charges from constant bombardment. If you picked up a shard in your hand, its edges might sparkle faintly in ultraviolet, electrons freed and trapped again, a material constantly rewriting its own energy states. No creature could touch it bare, but machines might harvest it as a natural insulator, geology doubling as shield. Not all alien chemistries are harsh. Some are delicate, ephemeral, built of interactions we rarely consider. Boron nitride, for example, builds lattices as tough as diamond, but under alien conditions it could form entire crusts, pale and smooth, shining like porcelain. Unlike carbon, boron nitride resists oxidation. It reflects heat, it glimmers faintly with ultraviolet light. A planet dominated by it would appear ghostly from orbit, pale shells of mountains glowing softly against darker skies. Step across such terrain and you would hear a porcelain ring underfoot, every fracture singing like struck ceramic. Fluorine expands possibilities further. In atmospheres rich in fluorine, perfluorinated compounds may dominate, slippery molecules with bonds so strong that heat alone cannot break them. Rains may fall as fluorocarbon droplets, slick, transparent, pooling in basins like liquid Teflon. Your visor would smear instantly with such rain, droplets refusing to evaporate, sliding without resistance, impossible to wipe away. Such liquids are inert, but their presence transforms soil, preventing wetting, repelling chemistry, isolating life unless adaptation invents new strategies. In still stranger cases, surfaces may be paved with crystals of silane compounds, silicon bonded to hydrogen, unstable on Earth but persistent in reducing atmospheres. Such crystals are brittle, reflective, and faintly metallic, catching light in flashes that mimic mirrors scattered across plains. Each fracture releases hydrogen, feeding skies with slow trickles of fuel, a recycling between crust and atmosphere. A silane desert would glitter with harsh brightness, every dune sharp-edged, every step crunching with the sound of breaking glass. Machines landing there would need to shield against both sharpness and gas, geology and atmosphere conspiring to resist. High in some skies, condensation may form flakes of exotic nitrides, aluminum nitride or silicon nitride, falling like pale snow. Unlike water flakes, these are dense, heavy, sharp. They pile quickly, compressing into stiff layers that resist melting. Cliffs of nitride snow would shine blue-white, glittering under dim stars, slopes carved not by avalanches but by brittle fractures. Each step would crunch loudly, echoes carrying far in the thin, cold air, a soundscape alien in every sense. Yet beneath, pressure might squeeze these nitrides into even denser ceramics, hidden cores harder than diamond. And then there are oceans, not of liquids we know, but of liquid nitrogen, sloshing calmly under faint suns. At 200 degrees C, nitrogen flows as a fluid, filling valleys, shaping coasts, eroding rocks slowly. Waves there are slow, heavy, dull, moving under thick air without sparkle. Boats could float, but their hulls would become brittle in minutes, cold, gnawing through alloys, metal, snapping like glass. For life, such oceans would be an obstacle, yet for chemistry, they are laboratories, dissolving gases, building fleeting molecules that freeze again by dawn. Closer to stars, there may exist planets with crusts rich in vanadium or molybdenum, forming oxides with shimmering colors. Vanadium oxides can shift hue with temperature, changing from yellow to green to blue as bonds rearrange. Imagine an entire valley glowing one color at sunrise, another at noon, another at dusk, landscapes painted by thermal chemistry itself. Each rock would serve as a thermometer, each mountain a signal of shifting heat, geology as timekeeper of a planet's day. Such cycles could even influence climate, surfaces absorbing or reflecting starlight differently with each change. Even stranger are materials shaped by extreme cold. At temperatures barely above absolute zero, quantum effects dominate. Atoms huddle into Bose-Einstein condensates, phases where identity blurs. On Earth, such states last only in labs, in traps colder than space, but in shadowed craters near dead suns, whole pockets might persist. In such places, matter flows as a single wave, all atoms moving in synchrony, all properties exaggerated, all rules bent. A fragment of this state would evaporate instantly in warmth, but in its home it is stable, silent, alien beyond ordinary words. Beyond cold lies radiation, not as destroyer but as sculptor. In atmospheres near pulsars or magnetars, particles rain constantly, striking molecules into exotic isotopes. These isotopes may embed in crusts, glowing faintly with their own decay, turning mountains into natural lamps. Imagine climbing a slope that glows without fire, its stones warm not with heat, but with radioactive whispers. Such landscapes are both warning and wonder, hazards glowing gently in alien night. Not all alien matter is lifeless. Some compounds may serve as scaffolds for proto-life, minerals with catalytic faces, guiding chemistry into repeating loops. Clays here on Earth already teach molecules to assemble, and on alien worlds, other minerals may play similar roles. Boron-rich lattices, vanadium oxides, molybdenum sulfides, all may shepherd complexity toward order, minerals acting as midwives of biology. A pond edged with such stones might hum with chemical ambition, water or methane, carrying loops of reaction toward persistence. In such places, material and life are not separate, they are partners, chemistry writing biology into existence. Stranger still are superconductors under natural conditions, phases where currents loop without loss. In deep mantles, hydrogen-rich alloys align, electrons pairing into cooperative flows, magnetic fields surging outward. Such fields might be uneven, displaced, tilted, stronger than any iron core dynamo. Auroras would roar across skies, sheets of light covering hemispheres, storms coupling atmosphere and mantle. The material itself is hidden, but its signature is visible, the entire planet glowing with magnetism. There may be worlds where the soil itself is plasma-rich, constant discharges crackling under boots, electrons leaping upward with each step. To walk across such a plane would be to carry sparks in every direction, your suit glowing faintly, static dancing along every edge. These soils would be unstable, volatile, their chemistry written in arcs, not bonds. Storms above would only feed them, adding energy, recharging a crust that never sleeps. Machines landing there would struggle, every circuit interfered with, every measurement disrupted by the hum of electricity in the ground. Still stranger are planets whose crusts are liquid crystals, not random but aligned, molecules forming sheets that shift with temperature or light. Each sunrise flips alignment, colors shimmering across planes, polarization shifting with every degree of heat. Stand above such terrain and the very ground would shine in shifting rainbows, every step producing ripples of color. Unlike stone, these surfaces flex. Unlike polymer, they organize halfway between fluid and solid. The planet itself becomes a kaleidoscope, its crust a restless quilt of order and disorder. Deeper inside, perovskite variants may form, not just cages of oxygen and metal, but double or triple lattices, frameworks unknown here. These phases resist even our guesses, their structures predicted by computation but never built. Yet in alien mantles they may fill whole layers, stubborn, heat-resistant, building blocks of strange geologies. Earthly words like granite or basalt fail here, because these rocks are neither, they are new genres, mineral chapters yet unread. And even further, under pressures no anvil can mimic, electrons may abandon individuality, merging into seas so strange that ordinary matter seems like a simplification. Atoms themselves lose shape, nuclei squeezed into proximity, bonds rewritten into exotic metallic phases. Some of these phases may carry superfluid traits, frictionless, unbroken, flows without limit. In such cores, heat moves too efficiently, cooling planets quickly, altering lifespans of activity. We cannot yet describe them fully because they are not yet modeled, but nature already writes them, hidden deep, stable for billions of years. Above, skies host vapors we rarely consider. Silicon hydrides, phosphine, arsine, stibine, each unstable on Earth, but under alien balances they may dominate. Phosphine already hints at itself in gas giants, an uneasy signature that resists explanation. In richer atmospheres it could dominate, forming layers that smell acrid, green, alien in every sense. Each such molecule tells us that life is not the only chemist, that planets themselves experiment endlessly. And still we have not touched every possibility. The catalogue of alien matter runs wider than our words, deeper than our imaginations, longer than our patience. Time is the last ingredient, the quiet force that tests every material, stretching its patience, breaking its weaknesses, rewarding its strengths. On alien worlds, time is not measured in days or seasons, but in millions of years, and across such spans, even the hardest crystals yield. Even the most stubborn bonds find paths toward rearrangement. The stones that seem eternal today may be powders tomorrow. The gases that dominate an atmosphere may be buried tomorrow. The very crust that appears permanent may vanish into mantle currents. Time is the sculptor that never tires, and its lesson is that no material is immune, no matter how exotic, no matter how strange. There are places where radioactive decay plays the role of clock, every mineral carrying within itself a timer, slowly warming its surroundings, slowly changing its balance. Isotopes that formed in stellar furnaces billions of years ago now guide the fates of planets, their decay releasing heat, their remnants shifting chemistry. A crystal of uranium oxide in an alien crust is not merely a rock, it is a ticking note of energy, a hidden sun embedded in stone. Over billions of years, such rocks dictate whether mantles remain active, whether volcanoes breathe, whether atmospheres replenish. The very habitability of a world may rest on whether its materials still whisper with the faint energy of decay. But not all clocks are radioactive, some are tectonic. Crusts fracture, collide, subduct, and resurface, cycling minerals from mantle to mountain and back. Every cycle rewrites the faces of materials, basalt turning into schist, schist into granite, granite into sediments. On alien worlds, the cycle may be faster, slower, stranger, depending on gravity, water, or heat. A single mineral may play dozens of roles, each one a page in a longer autobiography, written by pressure and time together. Magnetism, too, leaves its memory in materials. As iron grains cool, they align with the magnetic field around them, tiny compasses frozen into stone. On Earth, we read these memories to map the drifting of continents, the flipping of poles, the restless wanderings of plates. On alien worlds, such magnetic signatures may tell different stories, tilts and offsets that betray hidden dynamos, records of mantles moving in silence. Every pebble on a foreign shore may be a journal, carrying the history of fields that once blazed and then died. Radiation builds stranger memories still. In crystals bombarded by cosmic rays, tracks form where atoms are displaced, scars invisible except under careful eyes. Over millions of years, such tracks accumulate, a diary of the universe's violent background. Pick up a shard of zircon on an alien world, and you may hold in your hand a silent record of every flare, every solar storm, every burst of stellar anger. The material becomes an archive, patient, indifferent, but faithful, carrying stories across ages. Even dust drifting between planets plays its role. Grains of silicate, carbide, or organic matter settle slowly, blanketing surfaces, filling cracks, smoothing cliffs. On some worlds, the dust may be diamond powder, on others metallic flakes, on still others complex polymers. To us, it looks uniform, but under microscopes, every grain tells a tale, each one shaped by its origin, whether volcanic, cosmic, or atmospheric. Surfaces are never bare. They are always clothed in these silent layers of history. But even without life, alien materials speak to us. Every spectrum recorded, every light curve measured, is a conversation between star, planet, and observer. We read these conversations line by line, sodium confessing in yellow, potassium whispering in orange, water writing in forests of dim bands. Each element a voice, each compound a tone, each atmosphere a chorus announcing what it is made of. To study alien skies is to listen carefully, to understand that matter has been speaking all along, waiting only for us to translate. The richness of alien matter is not only in its forms, but in its abundance. Diamonds on Neptune are not rare, they are weather, common as hail. Metallic hydrogen is not fiction, it is likely routine, enduring forever in giant planets. Superionic ices are not exotic, they are stable layers under crushing pressures. What we treat as impossible is simply ordinary elsewhere, made common by conditions Earth will never mimic. And yet we remain fascinated by these states because they remind us that our categories are parochial. Solid, liquid, gas, these are human labels, conveniences for kitchen and laboratory. But nature does not honor our labels. It slides between them freely, making hybrids, inventing phases, blending habits. Supercritical fluids laugh at the line between vapor and liquid. Superionic ices merge the stubbornness of crystals with the mobility of conductors. To study alien matter is to learn humility, to admit that our words cannot contain all of reality. Every world is a gallery, then, a collection of artworks sculpted by gravity and heat. Some galleries are dark, their works hidden in mantles we cannot see. Others are flamboyant, their skies painted in strange colors, their surfaces glowing with molten seas. Each world a chapter, each chapter a reminder that the universe does not repeat itself lazily but experiments endlessly. And in that experimentation we find hope, because variety is not an obstacle to understanding, it is the very fabric of discovery. The more we see, the more we learn that matter itself is the universe's language, spoken fluently in every star system. Now consider what happens when materials interact with life. Here on Earth, bacteria alter minerals, drawing iron into chains, weaving calcium into shells, sculpting silica into diatoms. Life is a material engineer, shifting geologies in directions planets alone would not take. On alien worlds, other strategies may exist. Organisms building shells not of calcium carbonate but of sulfides, or of carbides, or even of glassy silicates. Forests of alien coral could gleam like obsidian, plains of shells could ring like porcelain under boots, mountains of fossilized chemistry could rise as monuments to persistence. Life and material entwine until neither can be told apart, each shaping the other's destiny. But life is not required for matter to express itself in beauty. Crystals grow with their own quiet grace, faceted faces, expanding atom by atom, repeating symmetries across scales from nanometers to mountains. On Earth, we call them gems, we polish them, we trade them, but on alien worlds, they are not jewelry, they are geology. A cave of rubies is not treasure, it is simply a stable state of aluminum oxide with chromium impurities. A plain of emerald beryl is not wealth, it is the outcome of pressures and fluids. The idea of precious is always parochial, a reflection of scarcity, not of intrinsic meaning. Alien skies are equally blunt in erasing our values. Where we cherish diamonds, Neptune rains them by the ton. Where we build technology on silicates, exoplanets may scatter them as vapor in their atmospheres. Where we fear sulfur, Io paints its entire landscape with it in volcanic strokes. The cosmos does not respect our categories. It simply arranges matter according to its rules, unconcerned with our sense of rarity or beauty. Every world is a correction to our assumptions, every planet a counterpoint to our narrow expectations. And yet, across all this variety, there is a deep unity. The same periodic table serves every world, the same rules of quantum mechanics, the same bonds of atoms. What differs is only context, the pressure, the temperature, the ratios, the time. From these few variables arise oceans of difference, from lava seas to nitrogen glaciers, from glass plains to metallic storms. It is a lesson in humility, a reminder that complexity does not require new laws, only new environments. We stand, then, in a universe of restless possibility. We know only a thin slice of materials, a narrow catalogue born of Earth's mild pressures and temperate skies. But we have already seen hints of more: metallic hydrogen, superionic ice, carbide crusts, clathrate cages. Spectra from telescopes show us sodium in distant skies, potassium on hot Jupiters, methane hazes on Titan, carbon monoxide on Pluto. Each observation is a window, and through those windows we glimpse landscapes stranger than imagination. Someday machines will land on those worlds. Drills will pierce their crusts. Scoops will collect their soils. We will not only see but touch, we will hold in gloved hands samples of matter that has never cooled at Earth's surface. Perhaps the fragments will crumble instantly, unable to survive without their native pressure. Perhaps they will endure, stubborn souvenirs of alien geologies. In either case, they will teach us, they will broaden what we mean when we speak of possible materials. And when we reflect quietly, it becomes clear that this search is not only about science. It is about meaning, about perspective, about our place in a cosmos where even the stones surprise us. Every alien crystal is a reminder that matter is patient. Every alien ice is proof that nature experiments endlessly. Our own bodies are built of the same carbon, oxygen, nitrogen, iron, but arranged gently in the narrow conditions Earth allows. We are not separate from this gallery of materials. We are part of it, one arrangement among countless others. So let the mind drift at this thought, that every alien material we imagine is already written somewhere, waiting patiently under distant suns. The universe is wide enough to host diamond rains and metallic storms, silane deserts and nitrogen seas, superconducting mantles and radioactive slopes. Each world is a lesson, each lesson a humbling, each humbling a doorway into deeper wonder. And as you close your eyes now, letting the weight of the day fall aside, you may carry with you the quiet recognition that matter itself is never finished. It keeps building, rearranging, surprising, teaching, and reminding us that we too are only one temporary form, here for a brief span, but still part of the same eternal chemistry. Sleep then, within this chemistry, sleep inside the story of atoms, crystals, clouds, seas, and stones. For even as you rest, worlds continue to turn, materials continue to transform, and the cosmos continues to write its endless book of matter.